Da-da-da-da. Check I'm live. Uh, uh, yeah, it should be okay. Hang on, let me check so everything's okay. Uh, yeah, it seems fine. So yeah, so what we're gonna do today in this stream is to hopefully finish this paper. I'm also going to hopefully do another live on gaming later because there's a lot of information out. GTA 6 trailer 2 came out. This is hopefully discussing that, but the aim of this is to talk about the maths and finish this paper off. So yes, last time we did up to question 8. We finished question 8. This one was about the depth of water in harbour and using a modelling with trig. Uh, yeah. Um, we're going to continue the paper. This is where it's going to get hard at this point, but we'll work through it together. Um, but as I said, the aim of this is to just go through it, to think about the thought process, how you should approach the paper, and think about how you should think about it essentially. Okay, so on question 9, so we have a curve which looks like in a really weird form. It looks like an implicit equation, right? Because there's no here because there is no direct expression for y equals f of x, right? There's a y there, there's a y there, so it's not exactly clear uh, what the expression is. So it's an implicit function, right? And it asks us to find a derivative. So what that should be screaming to you there is implicit differentiation. So let's just start with that then. So hopefully my right's not too bad. Well, I probably will be. So we are given x squared plus, oh, not plus, sorry, x squared minus 2xy plus 3y squared equals 50. So implicit differentiation, you want to differentiate with respect to x. So this on its own, normal, so 2x minus 2xy. Now, this is a product. So if you bear in mind that this is like if y is a function of x, right? But it's not clear what the function is because it's implicit. If you differentiate y, y is actually in terms of x, right? So y is also a function of x. So it's a product of two functions of x and y. Okay, so this is why we need the product rule here. So what we're going to do with the product rule, so bear in mind you differentiate one and add the other, then differentiate the other one and add the other. Okay, so you should remember that hopefully by now. You don't get the formula for it, but you should be very comfortable product rule, chain rule by now. But anyway, we apply the product rule here, so minus 2. Uh, okay, and x of y. So differentiate x first, which goes to 1, and then y, so just a good y. And then plus, now differentiate the y, so x stays the same. Now differentiate y, when you differentiate implicitly with y, you differentiate like normal. So differential y would be 1, but you always tag a dy by dx to it, okay? Uh, um, I guess that would be because uh, I'll come up with an explanation for that, but let's just continue the question. Plus 3y squared, that's just one function. So differentiate look normal, 3y squared would be 6y, but just tag a dy by dx on the end of it. So basically, it's exactly the same as normal differentiation of a variable, but you just tag a dy dx every time you differentiate y. That's all it is with implicit differentiation. And then equals 30. Well, that's a 50, sorry, but that's a constant, so that'll just go to 0. And so then what we can do is we can right, let's expand this first of all. So 2x minus 2y minus 2x dy by dx plus 6y dy by dx equals 0. And now the strategy for this is to group the dy's together. So dy dx are minus 2x plus 6y. And actually, we can put it to one side, move everything else to the other side of the equation. So it'd be 2y minus 2x. Okay. And then you can divide through. Okay, so to get dy dx on its own, you would want 2y minus 2x over minus 2x plus 6y. Now, everything's a factor of 2. So divide through by 2, y minus x over minus x plus 3y. Okay. So it looks pretty simplified, right? Then just go back to the question. What does it say? Y minus x over 3y minus x. So what you can do then is flip the signs by times it by minus 1 on each side. So this is the same as x minus y over 3y minus x, which to confirm is what they wanted. Y minus x. Hang on. 3y minus. We messed up somewhere. Let's pay attention to the signs here. So they want y minus x. So what happened here? Let's have a look. Oh no, it's the same. It's equivalent. Sorry. No, so I got a bit confused. No, this is right. Because this it's y minus x over 3y minus x. So exactly the same. Just I don't know. I got a bit I don't know distracted there. So just it doesn't really matter. It's the same, but yeah, just change the order. And yeah, you're going to the exact form it wanted. Let's read what the other question said. Now there's a graph to it as well, so that'll come into play. The curve is used to model the shape of a cycle track with both x and y measured in kilometers. The points P and Q represent points that are furthest west, north, east, southwest. West would be the negative x-axis, so that would be furthest west and furthest east. Again, furthest on the positive x-axis, so P and Q. And then it says use part A for an exact coordinates of P. Okay, so it doesn't look like they're given a lot to work with, but they're drawn these lines for a reason. They are tangential to P and Q, respectively, right? So tangent. So obviously they should know that a derivative is a tangent, right, at a specific point. So that will come into play here. So have a look at this gradient here. So this gradient is 0. Okay, so no matter how many times we increase x, this line will always stay the same. So it's not steeping anywhere. So m greater than 0 means dy dx has to be 0. Okay, and that's what we're going to do. So dy dx is 0. And essentially that's what we're going to solve. So dy dx equals 0 means that what we worked out has to be 0. Okay. Now with fractions, this can never ever be 0. The denominator, never ever. Divide by 0, just a no go. So the only way we can ever get 0 from a fraction is if the numerator is 0. So that means y minus x has to be 0, which means then for this to be 0, x has to be y. Okay. Um. Okay, so that's the information we can deduce. But then it's set to find the coordinates of P. Okay, well, so I think to find P, as always with any lines or find coordinates, you go back to the equation of the curve. Okay, so I think now that we know y equals x, that we can substitute it into here to get one variable. And I think that's the best approach. So let's denote the curve. So x squared minus 2xy. Curve is. If only I could know to how to copy and paste text. I'm not that proficient at this sort of thing yet. So that was the equation, right? X squared minus 2xy plus y squared is 50. 3y squared is 50. Okay, okay, let's change that. 3y squared. So we're going to substitute x is y. Sub x equals y. And what do we get? So let's keep the x. So x squared minus 2x. Now y is x of x squared. Look at here. For 3y squared, well that'll go to x squared equals 50. Oh, equals 50. Like terms. So 3 for 4 minus 2. So 2x squared is 50. Which means that x squared has to be 25. Which means x has to be plus or minus 5. So the x coordinate is positive 5 or minus 5. To work out which one, use the graph. So we can clearly see p is on the negative x-axis, which means it has to be negative 5. Okay. So p lies on negative x-axis. So x is minus 5. So p equals 5y. Well, we also know x equals y. So it's 5, 5. As x equals y equals 5 at p. And that's your coordinate, I believe. Did it say an exact form? Okay. Usually when I say exact, they want you to have it in. Oh god, what have I done here? They want you to give your answer in like a root or third or something like that, or fraction. So it's interesting. It says exact, but you just get a whole number. Also seems a tad bit easy for what was it, 5 marks? But I don't see. Yeah, dy dx should be 0 because the tangent of the curve. And you see, this is the tangent, and it's flat, so the gradient must be 0. Dy dx. I'm gonna check that actually. I'm gonna check that. I don't know unless I'm missing something. I don't know why it says exact coordinates. When you just get a whole number. Let me check that for a second. Uh, oh no! What? I'm a complete idiot. It's not flat at all. I'm losing it. I really am losing it. Oh god. No, it's not flat. It's the opposite. It's completely high. It's complete flat in the sense like it's not like slanted or anything, but Flat would be like that side, but this it's the opposite way around. The gradient is infinitely high then. So the gradient is completely okay. See, that's how you know if you got it wrong. Use the wording it gives you. That is wrong. But that's a good reason why we're doing all this. It's a good way to show where things go wrong. There you go. I knew something was off because it asked for exact coordinates. But anyway, m to infinity. So obviously, like before, we do the same sort of stuff, but obviously it's different now, not zero. So that would imply dy dx is infinity. Now, a number or something cannot actually be infinity. It's just a concept, it's a limit, right? But how would we think of it? So if this goes to infinity, remember this is a fraction. So again, a fraction only goes to infinity if the denominator, which is 3y minus x, goes to 0, right? So it equals, if you want infinity, if the denominator equals 0. Okay, so instead of the numerator being 0, we want the denominator to be 0, right, this time round. So 3y minus x is 0, which of course means that x has to be 3y. So then we do the exact same methodology, but obviously the numbers are a bit different. So instead we want a 3y, not just y. Okay. Let's get rid of this. So we have x squared minus 2x times 3y. That'd be minus 6x squared. Okay. Plus 3y squared. 3 times 9y x squared, which should be 27x squared, I believe. Yep, and that equals 50. Which should then mean collect like terms, so 22. Hang on, has to be 50. And then x squared has to be 50 over 22. So x then has to be plus or minus the root of 50 over 22. Okay, so, and the exact same reasoning, positive or negative. So, if it's on the negative, x has to be minus root 50 over 22. Okay. And because we know what x is, oh god damn it, we know what x is. We also know what y is because y is going to be a third of x. Y is going to, wait, no, done it wrong again. You can tell I'm very, very rusty. It's meant to be in terms of y, not x here. God. So y, x is 3y, so that'd be 9y squared minus 2y times 3y, that'd be minus 6y squared. So it's the same one. I think it's just no, actually it's not the same one. Anyway, we get that correct like terms. 6y squared would be 50. 12 minus 6. Y squared would be 50 over 6. Can we simplify that anymore? That'd be 25 over 3. Therefore, y would have to be the plus or minus root 25 over 3. And actually, we can simplify that anymore. So I get, okay, think about where the y coordinate is. So, if we go back, p is on, again, the negative y axis here. So we want the negative value for y here. Okay. So y would have to be minus, and actually we can simplify this. Distribute the roots to both sides. So root 25 is simply 5. So minus 5 over, and then root through, just leave it there. And actually, we can simplify it even more, rationalize it. So minus 5 root 3 over 3. Cool. And x then is 3y, which is minus 5 root 3. Therefore, p then is very simply minus 5 root 3 over minus 5 root 3 over 3. And that should be the answer. Yes. Okay, so say this is a really good exercise here. The maths isn't the trickiest, but the concepts you have to really check. And actually, the question does help you a little bit because you read it like, usually when it says exact, you want like a fraction or square root or some or third or something like that. So if you get like a nice answer, you probably got wrong somewhere. Also, make sure you know differences when I be flat. So this line, if it's completely flat horizontally, the gradient 0, but if it's vertically flat, then m is infinity. When I said flat, I assumed it was horizontal, when obviously with eyes, you can see vertical, so it would be infinity. I got confused when I said it was flat, and I immediately jumped to 0. That's just my wording now. I was thinking too far ahead. That I didn't think. See, you have to be with these exams. You have to be really, really like careful. You need to take your time here, or else you make silly mistakes that I did here. And also with that, I assumed that it was X and Y. It should be nil. Anyway, lesson learned now. Okay, so we did that. So we found P. So that was 5 marks. Explain briefly how to find the coordinates of the point that's furthest north of the origin. So the what this point here. Okay. Furthest north. Okay, interesting. Well, from this is where we think about it a little bit. Really stare at the graph. Uh, Furthest north. So it's not that point actually. That's wrong. So furthest north, obviously, it's the highest y coordinate. So actually, it's not there. It's around here. Okay. And actually, what that would mean as well is the horizontal tangent this time. It's kind of like the flipped like with this. So actually, instead of the vertical being here, a vertical tangent, you'd get a horizontal tangent. If I can, yeah, it's really awkward to draw on this. Something like that horizontal, really badly drawn, but a horizontal tangent. Okay. So furthest north would mean the highest y coordinate. So again, if you want the maximum, you're going to deal with a stationary point like these. These are stationary points. Actually, no. Actually, that no, they're not stationary points because they're not 0. That's no, but this is because it's a horizontal tangent, which means the gradient must be 0. So dy dx is 0. So this time, if you were to find the coordinates of the furthest north, you would want to find furthest north point. You want uh, the point with maximum y coordinate, okay, or maximum y value. Uh, which at this point, as we've seen, which at this point, dy dx is 0. Okay. Um, because it's a horizontal tangent. Okay, so instead of solving dy dx is infinity, dy dx is 0. So use use y minus x equals 0, right? Not to it did say not to carry out the calculation though. So use minus x 0 to find points. To find the coordinate. Okay. So we're not carrying out the calculation, but it would be very, very, very similar to what we did in part B. Okay, that was a really, really fiddly question. Really makes you think, actually, especially part C, actually, to think about what you'd need to do and think graphically. I like that sort of question. Okay, so what have we got here? So the height above ground of a passenger can be modelled by the differential equation. So whenever it says it's a differential equation or you spot it's a differential equation, look at the marks because you'll almost 99.9% be required to solve it to find something out. Okay, and actually that's what it's asking you to do in part A. Because look, 5 marks, so you're gonna need to solve a differential equation. So before what's we'll deal with the other information in a minute, but it's a good idea to just solve it first. Obviously, you'll get a general solution, but we can use this information to work out any missing constants or anything like that that arises. But anyway, so let's just rewrite what we've given here. So dH by dt is h cos 0.25t, and this time it's in radians. So if you're in this exam, you'd now need to convert from degrees to radians. Just to check. Anyway, so we got given this. Now, in normal A level, you'll only be required to separate them. And actually, it's really nice because you've already given it in dHdt equals something. So it's very easy to spot how to separate the variables. Okay, so as always, you want to move the dt to the other side. H cos 0.25t. It shouldn't be too bad to spot how to separate it, but I'm going to break it down a little bit just to make it clearer. 0.25t over 40 dt. So that's all they do. That's the step you really want to do with these differential equations. Have a dh dt. You want the dt dx's, the two dt's, if you will, the two different variables on either side. Okay, and then it follows from there. So now you want to split you want to put all the variables on the same side, same variables on the same side. So h. Okay, so you do want to divide through by h to put it on that side. So 1 over h dh, and actually we already have dt on this side. So it's going to be 1 over 40 cos of 0.25t dt. Now, the beauty when you put all the little derivatives on either side, you can now integrate it both sides. So it's almost like a different operation. You can multiply both sides of the equation, divide both sides of the equation. This time you can integrate both sides of the equation because you got this dh here. So notice when you integrate f of x dx, that dx needs to be there. And that's kind of what you're doing here. Once you've got the dh there, you can integrate with respect to h, integrate with respect to t. Yeah, and that's the whole idea of these separable equations. That's the idea. Use again. You should think it's all logical, really, once you understand it. Um, use the variables. Use all this to guide you. Okay, to see what you can do next. So yeah, that's what we're going to do. So integral 1 over h dh equals, and we could bring this constant factor on the other outside of this one. 1 over 4e, the integral cos 0.252 dt. And yeah, so now we integrate one. This one should be very simple. We actually integrated this earlier in the paper already. The one with the reverse chain rule. Very similar question. The map you should recognise just goes to learn mod h, and then this is 1 over 40 of the integral. Now, integral cos will just go to sine. The signs don't change this time when you integrate. So it'll just be simply sine. However, because it's integration, it's the reverse of differentiation. When you have a constant kt or kx, instead of timesing by k with the chain rule, you want to divide by this number instead. So you'd want, if you want to integrate to, you'd want to divide by 0.25. So 1 over 0.25, and then it goes to sine, and obviously then you keep it the same. Okay, you can check this if you wanted to check that you're right. Differentiate this again. So sine would go to differentiate this. It'd be 0.25 cos 0.25t times by 0.25 over 0.25. You get cos of that. Okay, so that's right. So let's check, and actually we can simplify some stuff here. So put that into your calculator. 1 over a quarter will just get you 4. So then 4 over 4 would be 1 over 10 sine of 0.25t. Okay, now it's now we want to express it as an explicit function as a h equals da 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 da. Okay, so because we've got to learn here, we can actually raise the power here. So e to the and then we have to have a plus c, obviously, because it's indefinite integration, right? And with indefinite, every time, because integration is reverse differentiation, but this is now saying if we differentiate both sides, we get back the original integral. But if we differentiate constant, it goes to 0. So we also have to factor in a constant, a plus c. Okay, that's important. But yeah, so then we can use e. We can raise f to the power of e. E to the 10th sine 0.25t plus c. Now, we can actually, now, if you should remember the rule, and actually, I think it's in the formula book, e to the learn x will always be x. Okay. Um, so this is saying, well, if we were to, it would be mod h essentially, but I'll show you what you can do in a minute. Mod h would be, this. So let's simplify this. So e to the 10th sine 0.25t. And actually, what you can do here is as well, you can also say e to the c, because remember the law, a to the b, a to the c, is a to the b plus c. So because we're adding a plus c here in the exponent, we can split it up into a product, okay? Okay, cool. So actually, so what it's saying here is h would be plus or minus e to the c, e to the attempt sine 0.25t. Cool. But actually, we can do this is a constant here, and actually, this whole thing is another constant. We could call all of this another constant, okay? Uh, because we don't really care about what c is. We just want we don't. This whole thing is just a constant. It don't really matter if it's plus or minus. We're not solving for c or anything like that. It doesn't matter. So we just call it all an a. It's absorbed. The sign gets absorbed into the constant here to get another constant at the end of the day. So actually, we don't really need a plus or minus. We can call all of this an a. Remember, e to the c, e is a constant, c is a constant, plus or minus is a constant. Really, plus it's all a constant. Okay. So we call this a, which means h then is just simply a e to the 10th sine of 0.25t. And that's it. And actually, in general, when you got a log equation like this, usually when you solve differential equations, you're going to have learn y or learn h or mod h. Because when you integrate, obviously you need learn a modulus, okay? What you can do is, because of this, you can always just skip to h equals e to the c. You can ignore the plus or minus because it doesn't matter. Like I said again, it's all just a constant, and we don't care as long as we know it's a constant. We don't care which one it is. Just we need to know it's a constant. So if we absorb the plus or minus, so it doesn't matter. But yeah, that's the explanation behind that. And but notice, it's a definite. It's not every. There's no unknown constants, so we need to use information given. So it says the passenger is 5 meters above the ground at the start of the ride. So start of the ride is screaming T0 probably because T is the time from the start of the ride. So at the start, well, T is going to be 0. And I can't underline because I'm bad. So then the passenger is 5 meters above. So read the question. Height is above ground at H meters above ground. Well, it's above ground at the passenger. So that means H has to be 5. So this condition has to be satisfied with the function. So let's substitute this in. So h is 5 t0. T0 into expression. Make sure it's clearly a 5. There we go. The idea of this is we're going to find a. Okay, so 5 is going to be ae to the 10th sine of 0. Okay, because this will go to 0. And actually, that's saying that 5 then is going to be, well, what's sine of 0? 0, right? So then this will go to e to the 0. E to the 0 is just 1. So this says that 5 is simply a, which then means the full complete equation for h, the particular solution, if you will, is going to be, h is going to be 5e to the 10th sine of 0.25t. Now, hopefully, should be the right answer. Unless I made a mistake again. Let's have a look. AE to the zero point 0.1. Yeah, so 1 over 10, 0.1. It doesn't matter. You'll be fine with that. Then it says state the maximum height of the passenger above the ground. The maximum height. Okay. Notice it's 1 mark. So you do what you should not be doing is differentiating all this. You know. However, uh, what we are given, though, remember, we don't need to differentiate it, though, because we know maximum height is going to be implying DHDT 0. That's one way of looking at it. But actually, we're given this already. DHDTs will be given it in this flat form. So let's rewrite this again. So DHDT, we're already given. And it's kind of like the last question again. DHDT, what was it? H cos 0.25t over 0 over 40, sorry. I'm getting ahead of myself here. 0.25t over 40. Is that right? It's annoying to scroll down. Yes, so the maximum height dh by dt has to be 0, right? This has to be 0. Now we know we've already discussed this. For this fraction to be 0, that means h cos 0.25t has to be 0. Now, this means would h be 0 or cos of 0.25t 0. Now, it says the maximum height. It makes no sense for h to be 0 here. So this means h cannot be 0 here. So the only other solution here that we have to take is this, so cos 0.25t 0. No, actually, do, 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 do. So we could just find t, and then once we find t, we could substitute it into the equation, see what we get. So cos 0. It's a lot of work for 1 mark. I think there is definitely a better way of doing it. You can probably just jump if it's 1 mark. You can immediately spot that this has to be 0. And therefore you probably can also spot 0.25t. But I'm just breaking it down here. That 0 for this to happen, 0.25t has to be arc cos of 0. Um, but you probably can spot that immediately by going. This has to be pi over 2. Okay. But look, we actually don't need to work out t because we only need 0.25t because our function originally is only in 0.25t. So we can just substitute this directly. So sub 0.25t equals pi over 2 into h, and this should give us the maximum height. Okay. So this gives us the minimum height, clearly because it's still a stationary point, but this will probably then give us the maximum. You don't really need to test using second derivative, but let's just see what happens. Yes, so h then would be, we'll put it down in part A, would be 5e to the 10th sine of this. Well, 0.25t is pi over 2. And, sine pi over 2 would be 1. So 5e to the 10th meters. Does it ask for, and that'll be the answer because it's a constant. We can't simplify that anymore. Does it ask to give it in like a decimal form? Uh, Approximation? Yeah, I guess we can do. So let's do that then. So 5e to the 10th, whack it in the calculator, gives you about 5. Oh, God, it's looking at 8. 5.53 meters to 3 sig figs. It's a bit messy though. Well, actually, let's just spot another way. If you can actually just observe what the we know what the function is as well. We got down part A. What was it? 5e to the 10th sine 0.25t. Now we can work out the maximum of a function by considering what the maximum of all the individual functions are. So this is a composition of of e and sine. Well, actually, we know whilst e is unbounded, e obviously goes to infinity like that, sine is bounded like that. And actually, if we want to find the maximum value, we want to increase the exponent of x of e as much as we can. We want this to be maximum. And the maximum of this means we need the maximum of sine. Now, the maximum of sine will always be 1. And then 1 times a 10 will be e to the 1 over 10, which is what we've got here times 5. And that is a really short, and that's probably what they want you to do, justify that the maximum comes from the maximum of sine. And there's your answer. So we actually don't need this differentiation. However, we don't need to differentiate because we've already been given it in part A. Well, in the question even. And actually, it's not too much work to spot this either. So that's two ways of doing it. You won't get penalised or lose marks for doing it this way, but it's a bit long-winded. But if you are good at functions and graphs and you recognise that, you can argue quite easily, more efficiently, I guess, that the max is 0.25. The max is going to be 5e to the 10. Okay. Max is 5e to the 10th as sine of 0.25t has to be at most 1. Okay. So you're taking the maximum value of 1. But obviously, but yeah, that's how you would approach that. So then let's have a look at part C. And you really should be as well at A level. You should start to get to used to, especially when you go to uni as well. You really should be very confident about domain and ranges of a function, which is tricky. Don't get me wrong, but you need to be. But the best way to deal with domain and range, really just think about when of complicated functions like this or whatever. Just break it down. So the common ones you should be aware of is the domain and range of 1 over x, or the trig functions, or e to the x. You should know that e to the x goes to infinity, and it has an asymptote at y equals 0. 1 over x, well, think about it. As you increase positively, it will go towards, as x goes to infinity, this will go to 0. So it would look something like this on the positive one. Negative, as you go to like 1 over negative 0.001, you can try it in your calculator. That would go to 1 over minus infinity, which would go to, again, sort of 0. So it looks something like this. And actually, when it's 1 over 0, it would look like it's going to infinity. So the graph would look like that. So really, with these domain and ranges, just the best way to just think about the graphs and think about how you can maximize or minimize from that. But obviously, when that comes up, I'll probably do a video stream on that because I know that's a really tricky topic. But when the but I don't think it's the time or place to go deeply into that. We're going over the paper now. So then it says the passenger reaches the maximum height, which we worked out to be what was it, 5.5 something, for the second time at the start of the ride. After the start of the ride. Okay. So find the value of t. Now, actually, we kind of done this already. So let's read that again. Reach the maximum height at the second time after the ride. So we're interested when it reaches the maximum height 2 times, not once. So, so it comes to this, what we did in part B actually. So actually, part B actually might be the better way of working out, because now we could just reuse the working in part C. So we know that H is maximized, or H is what 5.53. It's maximum when cos 0.25t equals what was it? Oh no, was it sine? No, cos. When cos is 0. Okay. Uh, so essentially, we're just solving this. So we need to consider the solutions we get here. So that would mean 0.25t would have to be, well, we already know it's pi over 2, but think about the graph here. So consider the cos graph. It should look something like that. When you're solving trig, always think about the graphs. I think that's the best way. But anyway, so when it's 0, it first hits at pi over 2, then it hits here at 3, that's 270, or 3 pi over 2, okay? And actually, it also repeats every 360, or 2 pi. So we keep adding 2 pi's onto this, so then that'd be 5 pi over 2, then 7 pi over 2, and so on and so on. So then that would mean t then times by 4 would be 4 pi over 2, which should be 2 pi. 3 pi over 2 times 4 would be 6 pi, I believe. And then 5 pi over 2 would be 10 pi. And then you can spot the pattern again. Now, actually, it says that t is the second time it reaches 0. Okay. And no, reaches the maximum height. So we want the second solution here. So that means t has to be 6 pi seconds, okay? To get the maximum height the second time after it starts when t equals 0. Okay, so the second solution from from 0, that's the first solution. That'd be the second one. Then obviously the third one would be that one. The fourth one would be the next. But we want the second one here, so we want 6 pi. Okay, so that's where that comes from. So it's a simple trig solving, but it's only 2 marks. So that should be it. I don't know if they want it in decimal form. I guess you can, but that's pretty exact. If you wanted to, I guess. So you wouldn't get penalised if you decided, if you give the exact form and the decimal approximation just to cover your back. It only takes like 2 seconds. It's equivalent also to 18.8 seconds to 366. But I think you should be able to get away with either way. Give it as a decimal or give it as an exact form. But you can never really go wrong with exact. And that's the answer. So 11, 11, 11. All 6 marks. So very clearly it's a binomial expansion one. So when you got binomial, you really should be aware of the formula for this, which is in the formula sheet. So the formula you expected to work with, if it loads. Have we got it? Nice. Okay. You know when I said in the formula book, e to the ln x is always or identical to x. But this is the same. It's just a slight variation. So e to the x ln a. Well, use log rule. So e to the ln a to the x. And now we can apply this. So then that's a to the x. So you can easily use this to get to this, okay? But yeah, so that's a side note. Let me get rid of that. When we did that, when we did that ln h, and then we used e to the ln h to solve differential equation. Okay, so here, so this is I'm surprised you get this one actually. It's quite interesting. I thought you'd have to know that one. Okay, so you get a plus b to the n. So you get two different types of binomial expansions. This one, but bear in mind, this is the AS version. This condition is very important. You need to pay attention to both conditions. They're very, very important. N, this weird n, is a natural number. So that's telling you you can only use this expansion when you have positive integer powers. So a plus b to the 1, a plus b squared, a plus b cubed, a plus b to the 4, and so on. But what we've got here, what you pretty much always, you very, very rarely only be asked to work with this. You'd always be expected to work with fractional negative powers. But this is the formula you're going to want to use here. Now, this is used for all n, okay, that are real. So you're going to probably use this all the time. And actually, I'm pretty sure, I don't know, you might be able to use this to get back to this, perhaps. I don't know, but anyway, I'm getting a bit sidetracked here. You're going to want to use this. This one, this formula is going to be crucial for any binomial question, pretty much. Now, I'm going to test it here. Can I copy and paste this? I don't want to copy all this out. Hang on, let me just test this. No, I don't want to write on it. There we are. Can I not like copy and paste it? No. Text highlight, perhaps? No, that's not helpful. Nah. God damn it, what have I done now? What have I done? Oh man. I don't want to highlight it all. What am I doing? God, I'm lost now. Yeah, it's my first, well, second time I guess, but really my first time dealing with a program like this. I didn't mean to delete it. Ah. Okay, I'm just going to copy it. I'm not going to faff around. So you need to be aware of the following formula. You should pretty much. Hang on, now I need to write on pen. 1 plus x to the n will be. Let's copy it term by term. 1 plus nx plus n minus 1 over 2. Right, it says 1 times 2, so I guess I write it down. It should be x squared, I'm pretty sure. Plus plus dot 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 plus, and so this is exactly how it says in the formula. So n minus 1 dot dot dot. So the repeated product up to n minus r plus 1 over. That's probably going to be r factorial. Let me check. Yeah, r factorial x to the r. Okay. So that's the formula as quoted in the formula book. So when you use binomial, you're going to need to somehow get it into this form. Okay. So let's do that then. So we are given this expression here. So we are given 1 plus 4x over 1 minus x. Uh, Pretty typical type of binomial. They want you to manipulate it into this. Okay. So that's what we're going to do here. Well, this is going to be the same as saying I can distribute the roots. Obviously, 1 plus 4x over root 1 minus x. And actually, then we can convert this as follows: 1 plus 4x to the half using index laws. And obviously, it's a fraction, so we have a negative index. 1 plus 4x to the half times by 1 minus x to the minus the half. Okay, so they're both looking very similar. They're both in the same form, actually. So it's just that 1 plus x. Now, x here is going to be plus 4x, and here x is going to be minus x. Okay, but they're both now, we can pretty much just substitute it into this formula. Now, let's pay attention. So it says, to show that. Now, notice this goes up to x squared, so we should use that to guide us here, to show how many terms we go up to. So, if you think about it, this is going to be 1 plus nx plus something x squared. And then this is also going to be 1 plus nx plus something x squared. If we then we're going to multiply it out, we're going to need to go up to x squared here and up to x squared here. Okay? To make sure we get every single x squared term, so that we get the answer. So that's what we're going to do here. So 1 plus 4x. And if you're unsure, you can just do a few terms and then see what happens. But yeah, so this is going to be, using this formula, up to x squared, well, 1 plus nx. Now, n is a half. If we want to, actually, you can write n a half. You can write 4x for here instead of just x. And actually, r tells you how many, what the power you want to go up to is. So if it's x squared, r is 2. Okay, if you want to be really clear to show what you're substituting, but you can just jump right in. So nx is going to be half times 4x, so that's going to be 2x. And then plus n minus 1, that's going to be half of a half minus 1, that's going to be minus a half. And then 2 times 1, that's just 2, x squared. Okay. No, not just x squared though. 4x all squared. So let's write that. Be very clear there. So that'll simplify to 1 plus 2x. Plus, okay, so we have half times minus a half. That's going to be minus a quarter divided by 2. So that's going to be minus an eighth. I believe you can check that in the calculator if you're unsure. Yes. And then 4x squared will expand to 16x squared. And actually, let's just simplify that once more. 1 plus 2x minus 2x squared, right? Likewise with this. So then we're going to get, what was it, 1 minus x to minus a half? Is that what, yeah, up here. So that will go to 1 plus nx. So here, n is going to be minus a half. We're going to deal with minus x instead of just x, and r is 2 again. Okay, so 1 plus nx, that's going to be half times minus x. That's going to be minus a half x. Plus n of n minus 1. Now, minus a half minus 1, get you minus 3 over 2. And that's going to be minus x squared over 2. Okay. And actually, that simplifies to 1 minus a half x. Okay, so what's going to happen here? So, plus 3 over 4 over 2, it should be plus 3 over 8. Now, minus x squared just goes to x squared because minus times minus goes to positive. And that should be the answer, I believe. So actually, what the product is now, what was it? 1 plus 4x to the half. 1 minus... That's going to be the product approximately to what we just worked out. We can substitute both approximations in. So use this one, so 1 plus 2x minus 2x squared. 1 minus a half x plus 3 over 8x squared. And actually, now you can see what you're doing. You know, when I talked about when you expand the brackets at the start to work out how many terms you need. Notice that we are going to have a constant up to x squared, a quadratic, and another quadratic. So if you multiply two quadratics together, you you need to ensure to get x squared from this. You're going to get a constant times x squared or something like that. So you need to go to x squared on both of them. If that makes any sense. But yeah, so now we just expand it. So you get this is still approximate to 1. Expand all the 1s first. 1 minus a half x. Plus 3 over 8x squared. Plus 2x times 1 plus 2x minus a half x. That would go to minus x squared. Now actually, x times x squared, it goes to x cubed. The answer only goes up to x squared, so we don't need to do that product. Okay, we can ignore that. Okay, so we only need to go to x squared with this expansion here. Again, so we've done all that. So now minus 2x squared times 1, so it's minus 2x squared. And then minus 2x squared minus a half. Well, that's going to be x cubed, right? So we don't care about that. And actually, that should be our answer. So it should be 1. Let's collect like terms. So 3 over 8, x minus a half, x. Should get you minus an 8. But then we have a plus 2 as well. So minus an 8 plus 2 gets you 15 over 8 apparently. And then minus x squared minus 2, that should be minus 3x squared. To double check we're right, let's go to the answer. Ah, what have we done wrong here? Okay, so interesting. Where have we gone wrong? 5 over 2x minus 5 over 8 x squared. Interesting. Okay, obviously this is always good to show where our answer's gone wrong. So yeah, we still want to go to x squared. Let's check our expansions right then. So it's a form. Always double check the form, and that should be right though. Yep, cool. 1 plus x to the n. Okay, let's double check the formula. Our multiplications right. So 1 plus nx, so that's going to be a half times 4x, so it's going to be 2x, right? Plus nx, so n of n minus 1, that's going to be half times minus a half over 2 of 4x squared. So that should be 16x squared minus an eighth. 16 over 8 should be minus 2. So I think that should be okay, I believe. Let's check here. So 1, so plus nx, negatives, bloody signs. Minus a half times minus x would be positive a half, not minus a half. Okay, there we are. So that's that's where we've gone wrong here. Always check your signs. Even the most basic mistakes trip you up sometimes when you're doing maths advanced. Always check your working. But yeah, there we are. So let's change your answer up. So plus a half. Shouldn't need to adapt too much though. So 1 plus a half x squared at minus plus 3 over 8 plus 2x plus uh, x squared. 2x times half x should get you x squared. That'll get x cubed. That ain't interested in that. And then minus 2x squared times 1. That should be that. So you should get but I don't think that's still right actually. Anyway, let's do that again. So 1 and then a half x plus 3 over 8 plus 2. Gets you 23. Oh, God, that's not right either. 23 over 8. Um, Interesting. Very interesting. Did we copy the function wrong by any chance? I'm going to put it past with 1 plus 4x over 1 minus x. No, it's the right function. 1 plus 5 over 2x minus 5 over 8. Interesting. Okay, let's check we're right. 1 plus x, 1 plus 4x to the half. It is a half because it's just a square root, right? Not a cube root or anything. No. Looks okay. That looks fine. Distribute the root. Say it's a half over half, and then put that minus the half because it's reciprocal, and your times in it. Okay. Then you say 1 plus 4x to the half is 1 plus nx. So nx will be half times 4x, which should be 2x. Okay. Double check that's right. The sequence. Yeah. 1 plus. Yeah. Okay. And then plus n here. n minus 1 over 2x squared. So n is again half of minus a half over 2 times 4x all squared. Let's just double check. That's right, I'm pretty sure it should be like 1 minus a half over 2 of 4 squared. I get minus 2, yeah, minus 2x squared here. So yeah, that should be right. What about this one again? So 1 minus x to the minus a half. That's going to be 1 plus nx. I've already dealt with this size. So n's minus a half, and x is 1 minus x. So nx will be minus a half times minus x, which should be half x. And then this, let's check that fraction's right. Minus a half, so n is minus a half. Minus a half minus 1 should be minus 3 over 2, yeah. Over 2 of minus 1 squared gets you 3 over 8. So that should be right. So it's expansion then. Okay. Okay, it's check expansion. So yeah, that's what this boils down to, the product of this and this. So have we substituted it right? 1 plus 2x minus 2x squared, yeah. And 1 plus a half x plus 3 over 8x squared. So 1 times 1 is 1. 1 plus a half x. 1 times a half x is half x. 3 over 8x squared. Ah, there it is. I just didn't write it down. I'm an idiot. That's x squared. That explains it. Oh my god! I just didn't add an x squared there. I'm taking the most simple mistake. My maths wasn't even wrong. Just because I didn't write it down. Oh my god. The most stupid stuff is this is again, I think this is really a crucial learning curve to anyone watching. You really got to take your time and really pay attention, check your answer. And don't do slip up like I've done. Like, check you don't miss any squares, check your signs. I'm doing all the rocky mistakes in this one, all of it. Okay, hopefully now that should come out. So that should be 1. Then add a half x, add 2x. That gets you 5 over 2, which I remember that being there. Plus 5 over 2x. Plus 3 over 8 x squared. Plus x squared minus 2x squared gets you minus 5 over 8. And that hopefully should be what they got in the question. Okay. Yes. Oh man. 6 marks as well. Okay. Oh my dear. Oh dear, oh dear. Okay, got them in the end. The maths was right there. Well, I mean, technically it's wrong, but it's because of the sign and I missed the power. Anyway, so then it says a student substitutes x is a half to both sides to find an attempt for root 6. And this is a very, very common thing. If you look at the textbook or whatever, practice exam questions, you will not really often just you find an expansion and then leave it there. The examiners will want you to use the expansion or criticize it. They want you to examine it in some way. This one, he wants to investigate to find an approximation, which is quite common. So it says, why should not you, now notice it's in bold, should not use x as a half. Okay, so with these type of questions, they really want you to consider the validity. So this is why I said in the formula book, pay attention to this bit in the bracket. You can only use this formula when this holds true. So mod x is less than 1. So, n is a real number. Well, n's a real number because it's a fraction. But mod x or mod of 4x. So, mod 4x has to be less than 1, and mod of minus x has to be less than 1. So you can bring it to both. Bring the 4 out. That's fine. Because it's a positive anyway. So 4. So that would mean mod x has to be less than a quarter, and not or, but and. Well, x has to be less than 1. Okay. So what it's saying is x is a half. That's what it's asking us to use. But however, mod x has to be less than a quarter. So if we were to combine them together, be able to use the expansion as a whole, combine it to so if x less than 1, but x also has to be less than a quarter, well, x has to be less than a quarter, right? However, so x, if x is less than a half, x equals a half, sorry, I'm chatting waffle. Well, a half is greater than a quarter. Therefore, expansion will be invalid. Okay, which would mean the expand. Oh God. So that means if we were to use expansion, it would not get an accurate answer. It would diverge. It would give something completely different. So we can't use it. It gives us the wrong thing. So we might have to make sure mod x less than a quarter. So obviously that would mean minus a quarter. X has to be between minus a quarter and a quarter. But a half is obviously outside the range. So we cannot use expansion. Okay. Okay. Yes, but also there was something else I wanted to talk about here, actually. Uh, and actually, on the topic of I'll probably do this at another time, but to quickly explain as well. Sometimes then I know in 2019 I asked this. If I ever do that paper, I'll do it again. But uh, sometimes you have to think about how accurate the expansion is as well. Yes, so if x is less than a quarter, yes, you can use it. It will technically be valid. It would eventually converge to the value because this series here, this expansion. Actually, I don't need to scroll up. This this expansion here is actually it's infinitely many terms. It converges to what this value is in the bracket. Okay, if you were to plug in x is like a quarter, or well, x is like 0.1. If you keep carrying this on, this will also get to 0. Well, 1 plus 0.1 to a half or something. This would also get to the same answer eventually. It will converge to this value here. It's like a geometric series. Well, it is a geometric series because it's the same thing. So geometric series with the common ratio is less than 1. Um, then it converges. Exact same sort of thing here. It's a type of geometry, right? So it will converge to the answer eventually. However, there are two factors that affect how good a binomial approximation is. First of all, very clearly, how many terms you use. And that should be a fairly obvious one. So if I only went to x squared, that would not be as a good of approximation if I use, say, x to the 7 or x to the 8 or x to the 100. Okay. So that's one factor that affects how good a binomial estimation is. But the second one, which is not thought of, I guess, as much, and it did come in 2019, how close x is to 0. Because because it affects the rate of convergence. So if x is close to 0, so what, I guess the best way to think about it is if I keep adding polynomial terms, 1x squared, as you get when you get closer to 0, um, obviously, say if I had 0.001 and then I had 0.9, for instance. If I did that to the 5 and I did that to the 5, well, actually, this actually put it in the calculator. It's too small. It's too small. It won't convert to a decimal. You can only have it in standard form. Whereas this 0.9 to the 5, it's 0.59049. So actually, this is still it doesn't converge to 0. Okay. So the rate of convergence when you have a higher value of x is slower than when you have a value closer to 0. Okay. So actually, what that means is if we have if we pick our x value for an approximation that is closer to 0, that will give a better approximation as it will converge faster. And what that also means is you will need less terms then because it converges quicker. Because any terms after, say, x squared, if we had x cubed plus x to the 4, well, as we've seen, if it's close to 0, this will pretty much be 0 as well. So adding terms is near negligible. Whereas if we had 0.9 to the 5, that would be 0.59 something. So it still affect the answer if we have a larger value of x. Okay. So that's a very, very important one. You need to check if first of all if an x value is valid, if it falls into the range of mod x less than 1, but also consider how, if it might ask anyway, how effective the approximation is as well. So it can be valid, but it might not converge quickly because of these two factors. You use less terms or the x is quite large, so it won't converge to the answer. Or give a better approximation, okay? And that did come up in one of the past papers as well. It gave you two values of x and it wanted you to compare which one you should have used, but both were valid, but obviously one gives a better approximation than the other. I just wanted to give that explanation because I think it's very overlooked when it comes to approximations of binomial, and it can come up, and it has done. So, and also just to make you understand it a bit more. So yeah, but the reason here is simply because half falls out of the range of validity. So half is greater than a quarter, so it won't be valid, so you can't use it here. But then it says effectively use it to find the approximation to root 6. So now we find a new approximation. Okay, so let's substitute x as a half in. And actually it's best I think with these type of questions, it's best to sub it into the original one, not the index version. So obviously 1 plus 4x over. Actually, no, it was a whole root, wasn't it? It was root 1 plus 4x over, what was it, 1 minus x, I believe. And actually, so let's do it first. So 1 plus 4, 1 over 11. Let's just see what happens, okay? And the idea is, remember, is to get to root 6. That's the aim, okay? But we'll see what happens first and what you can do. Because often you can manipulate it afterwards. Okay, let's just bring all that into the calculator, right? 1 plus 1 plus 4, 11th. But 1 minus 1 over, 1 over 11. Did I write that right? 1 plus 4. It's 3 over 2. Okay. Now, obviously, that does not give root 6. That's not explicitly clear. Okay. But then I guess how could we get root 6? Anyway, let's just write this, a root 3 over root 2, that might help. Well, actually, you can rationalise this, can't you? So this is the same as saying root 3, root 2 over 2. And actually, if you remember your third law, root AB is root A times root B. You can bring this into 1. And actually, 3 times 2 is root 6 over 2. So actually, what we do here is, if we were to substitute this directly into the expansion, you would get an approximation for root 6 over 2. So actually, let's do that here. So root 6 over 2 would be 1 plus x, which would be 1 plus 4x, sorry. 4, 1 over 11 to a half, and 1 minus 1 over 11 to the minus a half. Okay, so that's the exact same. So bear in mind, this what we worked on part A, this is exactly the same as this, okay? And therefore it's exactly the same as this when you substitute x in, okay? So yes, so let's substitute it into the expansion we found in part A. So that is what 1 plus 1 plus what was it, 5 over 2 x, was it? And that x is going to be 1 over 11. And then I believe it was minus 5 over 8, was it? Of 1 over 11 squared, x squared. Let me just check that's right. Was it 5 over 2 minus 5 over 8? Cool. Okay. Yeah. So then, bung that into the calculator. What do you get there? 1 plus. You actually get well, you do get a fraction here. 1183 over 968. Cool. But this gives you approximation of root 6 over 2. So to get root 6 on its own, you need to double it, okay? So it's 2 times this. Cool. God damn it, get off me. 968, which gets you what? Times it by 2. You get 1183 over 484, which as a decimal, does it say to how many decimal places? Give it as a fraction in its simplest form. Yeah, so that's a fraction simplified. The calculator will fully simplify the fraction, and that's what you get if you use a calculator. So that should be your answer right there. Okay, cool. And it's quite neat actually because it's showing. Obviously, we know root 6 is irrational as it's a third, but you actually get a fraction approximation there, which is quite interesting, I guess. Okay, we got some modeling. But again, very common. I've pretty much predicted with like 98% certainty. You will get a modeling with exponentials question like this. So again, just practice it. So it says the value. Um, okay, we have this equation. No, it's just two unknowns here, A and P. Okay, we got some conditions here. The value of the car was this on the 1st of January 2005. So the best way in this modelling is to convert it into math. So we know the value is 32,000 because it's in pounds. When T is what? So the dates. So T is in years. So this was when T is 0. Oh, the date is the first in 2001. So the year is here, right? When T is 0. Now, 1st of January on 2025 is going to be 1, 2, 3, 4 years later. Okay, so t is simply 4 here. So that's one condition. And also we're also given the value is 50,000 on the date 1st of January 2012. So that's going to be 11 years later. So actually, now it's just simultaneous equations, essentially. So the first part of part A is to find P and A. So yeah, just use this. So we are given V is AP to the T. And so substitute it in. So I'll call this 1 and 2. Sub 1 into... I'm gone. Sub 1 in. A very messy one, though, I must say. There we go. Well, 32,000. It's going to be AP to the 4. Okay, there's not much we can do here. Now let's sub 2 in. And now we get 50,000. It's going to be AP to the 11. Now, you could do it by substitution. I guess you could rearrange it and say divide by p to the 4. That's your a, and then substitute that a into there. However, if we divide if we divide this equation by this one, well, actually, AP to the 11 over AP to the 4, it's going to be 50,000 over 32,000. And actually, the A's cancel, and you then use index laws, so P to the 7. Bearing in mind, A to the P, let's use different there. A to the B over A to the C is going to be A to the B minus C. So you subtract the powers. Cool. So P to the 7 is going to be this. So it's going to be 50 over 32, which simplifies to 25 over 16. Okay. So therefore, P is going to be the 7th root of 25 over 16. There's not a whole lot you can do to simplify there because it's the 7th root. And yeah, it says to give it 4 decimal places. So that's the exact form, but then to give it 4 decimal places, let's work it out. I should. Oh yeah, there it is on the calculator. I was trying to work out how you get the 7th root there. 25 over 16 gets you 4 decimal places? 065831, so just 58 to 4 dp. So that's I, and then II. Then it says to find A. Okay, so we can show that A is approximately this value. Okay, so we found P, which isn't the nicest number, but we also have an exact form for it. So it says it's approximately, so there's not really much we can do rather than just simplify. We can't simplify, then just substitute it in and just plug it into the calculator. So just substitute P into any of these. So let's use the first one. So, so we know that AP to the 4 is, what was it, 32,000, was it? Just to double check. Yes. So then A of what? So the 7th root of this to the 4 is that. Therefore, A is going to be 32,000 over the seventh root of 25 over 16 to the 4, which gets you the number. Um, gets you this. So it gets you 24, 7, 9. Oh, yeah, 796, not 69. 796, comma there, I guess. 0.80 something, 8022, doesn't really matter. But it says it's approximately 24,800. So actually, to three significant figures, this actually is 24,800 to three sig figs. And actually, that just shows we did it right. So yeah, so that's it. Just some. That will always have. I guarantee an exam. You will be asked to give a model. Well, you'll be given a model, exponential, given some data, and you'll need to substitute it to find missing values. That will always be on there. I guarantee it. You would be asked to do something like that. Then it says, with reference to the model, for interpret the value of A and P. Very key word there. Yeah, you wouldn't really understand this, what it means here until you've done past papers or whatever. So what it means here is give the real life meaning of these terms. Okay. So I guess just think about it. And what usually with this, you want to consider what the initial value is. So when t is 0, v would be ap to the 0, which would just be a. So actually, a is the initial value of the car. Obviously, on January 2001, the first. Okay. Uh, at the start of the model. So that's the initial value of the car before it starts depreciate. Well, going vintage and then appreciating in value. And then P. Well, notice it's P to the T. So uh, if again you just consider the model, you this takes practice, and once you learn it, you see it the first time, you can apply it to other questions. But well, it's kind of like a geometric series in a way. You have AP to the 0. Then every year it goes up by A to AP, then AP squared. So you're going up by P every single year. So actually, what P is here is the 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 well, not the amount, because it goes up in, because that's implies you're adding it each year. We're not adding it times in. The amount, this, the multiple. How do I want to phrase this? The purport. No, not the purport. The the amount, the value of the car increases. Let's write that very clearly. Increases by each year. Uh, but I guess you want to make it clear you're not multiplying, not adding p. So I guess the uh, the multiple amount, I guess, if you want to be clear. But that's something I'd perhaps say. I don't know. The amount, the value of the car multiplied, the factor the factor of the value. I don't know. The factor the value of the car increases by each year, something like that. But yeah, just make it clear you're not adding p, but you're multiplying by p. Okay, because it's geometric, not arithmetic. Okay. So yeah, that's something I'd say. So you just have to be really careful here with how you word it when it says interpret. So that's what this means. It says with reference to a model, interpret a value. Okay, think about the real life implications. So here, okay. But yeah, hopefully you've seen that now. It's pretty similar to other questions. They love to ask this in stats as well. When they give you like a certain model or like statistical equation or probability, something they want to interpret that in context. As well, they love doing that in that. But yeah, that's how you'd approach that question. And then anyway, then he says using the model for part C. So we did part B on the up there. So part C. Um, Find the year which the value of the car first exceeds 100,000. So that means V would have to be above exceed. So it has to be strictly above 100,000. Okay. Uh, well then, just substitute an equation for V because we know what the formula is now. So we know that A to the what was it? A P to the T has to be greater than 100,000. And it says to find the first year. So the idea that we want is t to be greater than some number k. That's the idea when solving this. Okay, so first of all, we can divide by a. If you want to, I don't think they're too picky, so you can just substitute the approximate value for a in. Uh, so actually, let's do that. Let's substitute P and A. I don't think it'll be close. You can do it in exact values if you want. You can leave it in terms of P and A if you want to be precise or rigorous. But actually, because I've asked you to work that in part A, you can just use it probably. So P is 1.0658 and A is 224,800. So 1.0658 to the T is greater than 100,000 over, what was it, 24,800? Was that the numbers we're working with here? Yes, and obviously that would be what if you put that into the calculator. Just so if people aren't confident with like the algebra of working with letters like this, you can just substitute the numbers in if you struggle with that. Okay, well that's saying it's 125 over 31 and a calculator. Okay, so now actually we have it in the form uh, a to the t is another number. So a number by the variable is a number. So actually we can just use logs here. So and we can use when you do inequalities, you can use uh, logs here as long as this is greater than one, because then this won't and this is greater than one, because then this won't generate a negative number, so you don't have to think about flipping sides. Because bear in mind, if log if this number is sorry, and this number is greater than one as well. If the logarithm or ln is less than one, it goes to negative. So obviously, when inequalities, um, you have to then consider if you're flipping the sign, but it preserves the sign because it's positive because it's greater than one inside the log. Hang on a second, the door's going. Okay, back again. And yeah, so we get this. But actually, with log rules, remember, if you have a power, you can just bring it to the front. So t learn 1.0658. So we got the learn 25 over 31. And actually, then we can say t is greater than, and we can divide through by this. So you get 125 over 31 over learn of 1.0658. Cool. And that's it. So then, what numbers does this give you? So t has to be greater than learn of 125 over 31 over learn of 1.0658. 21.88. Da, 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 da. So there is some room of error there. So it's fine if you substitute numbers in. It's fine. It's not like 21.99998 or something. So it doesn't matter if you approximate a little bit as long as you get to this. But actually, it's 7 years, right? It's the first year, I believe. Let's go back. Yeah, so the year. So we need to deal with whole numbers. So, yeah. So that means we need to pick the first whole number. So, T would be 22. Okay, as a whole number. The first year after. What is it? So year 2023. Okay, because it starts at 2021. Or the model starts at 2001. Sorry, the model does not 2021. So 22 years after that, after is 2023. So that would be the year when it first appreciates. Actually, no, 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 I'm wrong. No, I'm wrong. Actually, no, no, that is not right. No, 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 no. That is not right. No, that's fine. So notice here. Let's get rid of these as well. This decimal saying that it's 21 years and another 0.88 of a year. So it's not 22 years. But what happens is it exceeds 100,000 pound the value of the car during in the middle during the 21st year, right? 21st year. So actually, so exceeds in year 2022. Okay, that's an important distinction to make there, because obviously, as model starts in 2021, and at the start of 2001, what did I keep saying 2021? 2001, and actually started specifically in the 1st of January, right at the very, very start. So uh, this will have to be in the 21st year. Okay. So the model starts in 2001. So after 21, well, not after, but uh, during the 21st year. So 2001, sorry, add 21, gets you 2022. That's what that, so actually it should be 2022, not 2023. Usually with this, they want whole numbers, but this one you have to be careful. It kind of deviates from the normal pattern. This is another key point with these exams. Sometimes they really love deviate slightly from like the usual type of questions. Because usually with this, you need to pick the first whole number. But this time you actually do need to consider the decimal. Um, and not round it because I did it there on autopilot almost. Like I just picked 22 because that's usually how the questions go. But no, if you read the question carefully, that's not what they want you to do here. So again, you need to be really reading the question and thinking deeply. Because sometimes what you used to know they deviate slightly. So you just need to be aware of that. I'm pretty sure it should be the right answer anyway. So 13. So it's just a big old 7 mark integration question. Lovely, lovely, lovely. So let's think of integration techniques. So it's just simply asking us to integrate this. Although I say simply, it's probably going to be complicated for 7 marks. Okay, so let's think about it. So obviously we can't use power. We can't use power laws, aside that. Can't use reverse chain rule. This doesn't differentiate to 2x or anything like that. This third. Um, we can't use. We can't just convert this into one like bracket like this. So a plus bx to the 1 minus or n. We can't do that because there's a product going on here. It doesn't really make sense to use the product rule either, I don't think, because this will get messy when you try. I don't know. Although maybe we could, if nothing else works, we can try for it. But I think the most suitable uh, thing we can do here is actually use substitution. I think because we've got a fairly nice looking function here, just 2x, and a slightly messy one here with a square root. I think if we use a simple substitution, so let's say u is to x plus 2, then we can get somewhere. But if it doesn't, then yes, we can consider alternative ways. And there might be multiple ways to do this, I don't know. But I think the way what it's screaming us to do is substitution. Um, and with A level math specifically as well, if it doesn't tell you what substitution to use, it should be a fairly obvious and simple one. So here, the most obvious one to use will be x plus 2. I think you could use squared as x plus 2 as well, but let's stick with this for now. Uh, we can adjust the substitution if it doesn't work out, but let's just go with it. So with substitution, especially with limits, you need to firstly, or an autopilot, work out the derivative. So du dx is going to be 1, and then just convert every piece. So remember, every piece of information here is in the x world, and we need to convert everything to the u world. Everything needs to be in terms of u, not x. So dx, kind of like rearranging the formula. Dx is going to be du over 1, so that's just going to be du. Okay. And so, and we need to change the limit. So x equals 2. Yeah, that is 2. Means that we need u to be 2 plus 2, which is 4. And x is 0 would mean u would be 2. 0 plus 2 would give us 2. Okay, now we can change our integral. So I integral equals what? So it's going to be between 4 and 2. For 2x, okay. Well, actually, we can convert 2x, can't we? Because if we know u is x plus 2, that would mean x is u minus 2. Therefore, 2x is going to be 2u minus 4. Okay. So that's going to be integral of 2u minus 4 of root x plus 2. So that's going to be root u du. Okay, because the dx is simply du, so we don't need to do anything there. And actually, what we can do then is use our third laws, not third laws. Well, yeah, third law, but our power rules, because root u is going to be u to the half, isn't it? And actually, you can bring a 2 out as well. We can factor a 2 out, make it easy for us. U minus 2. There we go. Of u to the half du. Now, actually, this is very, very nice to integrate. We can now start to use our AS techniques, our power laws, and distribute it to integrate using powers. Okay. So this is still 2 between 4 and 2. Of well, u to the 1 That's you should be able to do this automatically. However, break it down if you're not comfortable. So u to the 1 times u to the half, because remember this is a secret 1 here. That's going to be 1 plus a half. So that's going to be u to the 3 over 2. The same thing for here. Minus 2. That's just going to be simple minus 2u to the half du. Cool. And actually now we are in a position to integrate. So, if we were the integral, I'm going to be I'm not going to be really, I'm not going to be rigorous with this. I'm not going to like be precise. I'm just going to say, if we want to integrate a power of u to the, not u, sorry, of x to the n, that is going to be, so think about with integration, we times the power and then knock one off. So if I do d here, so we times power, and then we add 1 to power. Now actually, if you then want to go the other way, and that gets you uh, the derivative. That gets you y, the original function. Now, if you want to instead go backwards and integrate, so now we reverse. So we minus 1 to power first, and then you instead of times you divide by the power. So in other words, with this one, any polynomial again, it should be second nature, but to really go over it, if you have x to the n, so the power n, you'd want to knock one off and then divide. Oh no, sorry. No, this is minus 1 to the power. Sorry. When you differentiate, you knock one off. So this one you add 1 to the power, and then you divide by the new power. Okay, so that'd be 1n plus 1 x to the n plus 1. Okay, so you add 1 to the power n plus 1, divide by this power to 1. So that's the answer we get here. Okay, therefore the integral is actually now going to be 2 of 4 and 2. So we're going to integrate these three. Okay, so u to the 3 over 2. So that's going to be 1 over 3 over 2 plus 1. U to the 3 over 2 plus 1. That would be 5 over 2. Minus 2. U to the half. So that's going to be a half plus 1. That would be 3 over 2. And that would be between 4 and 2. Okay, because that's where our limits are. Okay, so minus 2, and then what I did, add 1 to the power, half plus 1, 3 over 2, divide by the power. Like I said here, 5 over 2, and then you divide by the power. Okay. Let's tidy this up a little bit. You can just bang it in into the calculator. Let's tidy it up though. 2, 1 over 5, that'd be 2/5. E to the 5 over 2. Minus 2 over 3 over 2, that'd be 4 over 2, I believe. 4 over 3, sorry. Okay, u to the 3 over 2. Oh, hang on, what's going on here? Between 4 and 2. Okay, so now we substitute our limits in. So 2 over 5th. Oh, god damn it. What's going on here? Go away. 2 over 5th of u, which is at 4, the upper limit first. 5 over 2 minus 4 3 over 2. And then minus the second part, 2/5. 2, 5 over 2 minus 4 thirds of 2, 3 over 2. And then you can bungle that into calculate and see what happens. And yeah, let's do that. Minus 2/5. Um, uh, okay, what is interesting here is actually type it in the calculator. It doesn't simplify it, it just gives you the decimal 3.6418, which tells you there's a lot of and actually look, the answer is this root here. There's a root inside, which tells us you can't really simplify it to get like an actual number. The calculator won't really give you a number like this, really. So that makes sense here. So what we're going to have to do is, what you can do here is type each individual term into the calculator and see if it simplifies it. So let's do 2/5 of 4 5 over 2 first. See what happens. It gives you 64 over 5. Okay. So let's do it term by term instead of whacking all of it into the calculator. If it doesn't give you a nice proper answer. 2/5 4 5 over 2 gets you 64 over 5. Minus 4/3 now. 4/3 of 4 3 over 2 gets you 32 over 3. Fairly nice fractions. Then minus 2, and I assume this is where it's going to start breaking down. 5 over 2 gets you a decimal. So that now we're going to need to use index laws here. So 2/5. So it's saying 5 over 2 is root 2 to the 5. Okay, so root 2 is 2 to the half. So 5 over 2, half of 2 to the half, which is root 2. Then you times it by 5. Let's just leave that there for now. Minus 4/3. And again, it's probably going to be the same sort of. Well, you could try it in the calculator, see what happens. So 4/3 of 2 to the 3 over 2 gives you a decimal. So you have to do that yourself. So 4/3. Again, it's going to be root 2. Okay, let's. Minus 4/3 of root 2 to the third to the 3. Okay, that's just index laws. There you go. And yes, and then we can simplify this. These calculators should be able to do this. So two lots of and this is why it's 7 marks as well, probably. Um, 64 for 5, 32 over 3. So this first bit here is 32 over 15. Nice. Minus now root 2 to the 5. Uh, do some rough jottings here to show. Root 2 over 5. That is root 2 times itself 5 times. So if I was to write it out, now actually this is just 2. This is just 2. So we're doing 2 times 2 times root 2, which is going to be 4 root 2. Likewise, if we have root 2 cubed, it's going to be root 2 times root 2. So it's going to be 2 to root 2. So actually, we can do a lot of simplifications here. So 2/5 of 4 root 5, 2, sorry, not 5. Why does it say that? Of 4 root 2, 2/5 of 4 root 2, well, that's going to be 8/5 root 2. Plus, because it's minus of a minus, plus, god damn it, plus 4 over 3 of 2 root 3, so it's going to be plus 8 over 3 root 2. 4 over 3 times 2 root 2 should be 8 over 3 root 2. Let's ignore that now. There we go. And yeah, so now you're almost kind of um, separating the root 2 terms with the normal terms. So let's do that. Now let's expand the bracket. So 2 times 32 over 15 gets you 64 over 15. Actually, no. Let's check this actually, because let's go back to the question. I remember. Oh no, yes. See, we need to consider a factor here, but let's just expand it first. It should be clear what to do after 64 over 15, and then plus two lots of this. So 8 over thirds root 2 minus 8 fifths. So 8 thirds minus 8 fifths is 16 times that by 2. And actually, it tells you we get 32 over 15 root 2. And actually, what you should spot is what we can factor out 32 over 15, okay? So that this is just going to be 64, which is double 32, so that's going to be 2. And then that's simply going to be root 2. And that should be actually the form it wants you to write it in. God damn it, if I can write the answer. God, this pen. Well, it's not really the pen, I think it's just me. Let's get used to it. But yeah, that's the answer there. It should be at 32 over 15, 2 plus root 2. Cool, and yeah, that's what they want there. Yeah, so that's the process. So again, think about what technique makes the most sense. Here's substitution. If they don't give you substitution, at least with normal A level, it should be fairly simple. Okay, and then go from there. Make sure to convert everything that's x in terms of u instead. So even the limits and the derivatives and everything in between. Okay. Yeah, it should be fairly straightforward once you do that. 14. I believe. I think this is the last question now, which is quite sad. But yeah, it's the final question of this series, this paper. And yeah, so it should be fair. It's probably going to be quite difficult, right? If it's the last one. Anyway, the cursive parametric equations. I think a lot of people seem to, well, here students or people in A level, they really, they're really quite frightened of parametric equations, especially when you involve trig. It's not. It's just. I don't know. It's just algebra, I guess. I don't know. It's not. I don't know. I think it makes a lot of sense. I'll go over it, but I don't know. I think it makes a bit of sense. But let's go over it. So we're given a parametric equation with the parameter t. Now it says show that all points on C satisfy y is da da da. Da. Again, this is quite common. They want you to combine y in terms of x and use that. Okay. It's quite a fairly nasty looking one, especially only 2 marks. You can use this to guide you though. So, what you should not be trying to do is explicitly try to like write t in terms of x or y. So like kind of inverse it and then substitute it. Don't do that. It'd be a mess. And as you can see here, it's quite grim looking. But actually, just reverse it in a way. So start with x, because y is in terms of function of x. Uh, kind of go step by step. So we know that x, it uses to guide you. So 3 plus 2 sine t. Well, that means x minus 3 is going to be 2 sine t. Okay. And actually, then if you square that, that's going to be 4 sine squared t. And then, x minus 3 squared, and then we need to minus it, because it's minus. That's going to be minus 4 sine squared t. And then if we do 6 minus x minus 3 squared, that's going to be 6 minus 4 sine squared t. Now, this apparently is supposed to be y, but it doesn't look in the same form. Instead of 6 minus 4 sine squared, we have 4 plus cos 2t. Now, notice we need a cos 2t. Now, actually, if you are a bit stuck, you can actually, you can kind of work with cos 2t, explore what happens. So cos 2t you should know is cos squared t minus sine squared t. Yeah, double angle. And actually, you can convert this using the identity cos squared plus sine squared is 1. That's going to be uh, 1 minus sine squared t. So actually, that's going to be 1 plus cos, sine squared plus cos squared is 1. So cos squared is going to be 1 minus sine squared. So that's 1 minus sine squared minus another sine squared. You get 1 minus 2 sine squared t. Okay. So therefore, 2 sine squared t is going to be equal to, make sure that's clear. It's going to be cos 2t, uh, well, 1 minus cos 2t, right? If we rearrange. Okay, move that 2 sine squared t, 1 minus cos 2t. And actually, because it's too much, you're probably just meant to know that or derive it. You won't get any marks for deriving this, unfortunately, I don't think. That's some trig identities you need to know. But anyway, we can use this. Now we actually have quite a link here, don't we? So we can say this is 6 minus, and if we've got 2 sine squared t is this, minus 4 is going to be minus 2 lots of it, right? Times this by minus 2, you get minus 4. And actually, that's going to be 1 minus cos 2t, which goes to 6 minus 2 plus 2 cos 2t, which goes to 4 plus 2 cos 2t. And actually, look, 4 plus 2 cos 2t is exactly y. So actually, we just get y. So actually, it's not too bad, really. Again, like just use just use the question to guide you. Literally, I think that's a good step with these type of questions like this. Work backwards if they give you this, and then you can kind of work it out that way. But never ever. Oh, I didn't mean to add dash though. Hang on, what am I doing now? There we go. I didn't mean to add a one there. Well, actually, what you should never ever do with these questions is kind of invert it in terms of t. So don't say like t is arc sine of x minus 3 over 2, right, of a half. Don't do not do that. Do not. That'll be an absolute mess. And it won't work out nicely at all, I promise you. So again, you're gonna have to use stuff like that. But yeah, it shouldn't be too complicated. Just some trig there as well. But yeah, for 2 marks, a bit nasty. I'm not gonna lie. But yeah, we've done that. So then it says for part B, there's 2 parts to it: sketch the curve and explain why it doesn't include all points. This is going to be the key point here. Notice that added that on the end. We'll talk about that in a minute. But sketch the curve C. Now they're giving you part A for a reason. Notice that this is the quadratic. And also notice it's in complete square form as well. So actually, you can use some information for that. When you're sketching a function, so what is it? Y is 6 minus, what is it? X minus what, sorry? 6 minus x minus 3 squared. Okay. But what I prefer to do with a complete square, always put the bracket first. I don't know, it doesn't really matter, but it makes it clearer in my mind. Minus x minus 3 squared plus 6. So the turning point, because it's a complete square form already, well, it's going to be 3 and 6. The way you work this out is, well, this is going to be a maximum as well. Is max because x squared coefficient is negative, because if you expand this, you're going to x squared and then minus it. Coefficient is negative, so has like a frowny shape, and hang on, And actually, that'll be the turning point there. But how you work out minimum or maximums with a quadratic and y completing the square works is, well, think about it. The only way you can vary y is if you vary what's in the bracket. Y varies with x, right? X is a variable here. If we want to, in this case, maximize, so the only way you can vary y is by varying x. Now notice this is all squared, so this is always going to be at least 0, right? However, this is a negative, so actually on the flip side, it's going to be always at most 0. It's going to be negative, okay? And so then the only way you can really minimize it or maximize it is if we take it to be 0, right? That'd be the highest value we can get here, no matter what x value we pick. We need to pick an x value such that the bracket goes to 0 so that we don't get a negative number. Okay. And so the best way to do that set to 0, it would be the minus of this. So 3 minus 3 gets you 0. So that's where that comes from. And then if we add 6, well, this is the variable part. This will always, and then we just add 6 onto it. So that's just a constant. So we maximize this as much as we can. So then we have to just add 6 at the end. And that's where the turning point comes from. And obviously, that's the x coordinate. That's the x value we pick to maximize it, which will be 3. And then the y value, obviously, once you substitute x in, that it will always correspond to 6 because this will always be 0 with this. Same with minimizing. If you want, a quadratic has a minimum point here if the coefficient is positive, so this would be positive instead. But then if it's positive, like I said, it will always be at least 0. So to minimize it, you want to pick 0. Okay, so then you make the bracket 0 always. Okay, to ensure you get 0 all the way, and then obviously add the constant at the end. So that's just a quick explanation demonstration of why you pick the turning point as it is with completing the square. But yeah, in this particular example, to go off track a little bit, it'll have this shape, so it'd be a maximum. Now, with sketching, you want, unless it says otherwise, you want to consider to help sketch your graph. You want to consider the turning points they are, potentially the nature, the maximum, minimum. Here, it's pretty easy to despise the maximum. Let me just write that clearly. You also want to consider where it intersects the y-axis and the x-axis. So that comes from the x. So when it crosses the x-axis, you want to solve y0. Okay. So that comes from 6 minus x minus 3 squared equals 0. So then you just have to expand it, unfortunately. So you'd get minus x squared. Then you'd get minus 6x, but then that's some negative up there, so it'd be plus 6x. Plus 9 minus 9, 6 minus 9 should get you minus 3. And actually, if you then solve it, you could use the calculator. Minus x squared plus 6 minus 3. You get these values here, so you get x is 3 plus or minus root 6. Apparently. Did I write that right? So then you can use the SD button. So this is about 5. Hang on. So that would mean x equals 5.449 or 0.55. So that decimal tells you roughly where the x intercepts are on the x-axis, the solution, the roots, right? That tells you roughly where they are. And then the y-axis intersection is simply the constant at the end. The y-axis intersection comes from setting x is 0 instead of y 0. So obviously it's the same. So x is 0 into here. So that's 6 minus 0 minus 3 squared. But that's going to be 6. Well, that's just going to be minus 3. Square, that'd be 9. So 6 minus 9 gets you minus 3, which is the constant here. Okay. Okay, so the other things you need to consider when sketching a graph in general, but that's all you need for quadratics: the turning point and the x and y-axis intersections. Also, for some graphs, you need to consider their asymptote. So, for example, e to the x would have an asymptote at y 0. You need to consider, and also obviously the reciprocal graphs. So obviously, like what is it that? They have to have a reciprocal graph at x equals 0 or anything else. You also need to consider the behavior when x goes to minus or negative infinity, plus or minus infinity. Now, with quadratics, it's obviously when it goes to negative infinity, it will keep going to infinity as well. Same with positive. The positive go to a positive infinity. So you don't need to do that. But some graphs, for example, e to the x again, when x shoots to infinity, e to the x shoots to infinity. However, that's not the best graph. However, when x goes to negative infinity, like I said, like an asymptote, the y goes to 0. So again, you need to consider the behavior of that. And that's what I would say. There's one or two other bits, but that's the main bits that you want to consider. And obviously, any discontinuities. So for example, 1 over x, you need to consider x is 0 as well. That'd be an asymptote, though. However, yeah, that's things you need to consider in general. But for a quadratic, that's all you need, and you should spot that this is indeed a quadratic. So we've got a big space here to draw it. Hopefully, my graph sketch is all right with this pen. Let's do it then. So let's label axis y and x. Should be GCC stuff, really. So we need to bear in mind our roots, first of all, 0.55 and 5.4. So let's say this is, what is it, 3 minus something? What's the root exactly? 3 minus root 6. And then this will be 3 plus root 6. So that's 0.55. That's and this one is what was it again? 5.449 or something. And the turning point is going to be at 3. So it's going to look over here roughly, just over the middle, 3 and 6. So that's where our turning point is going to be, a maximum turning point. And obviously we know the graphs are going to have a frowny shape. So we also know the y-intercept is at minus 3. Okay. So I'll just say that that is 3 and 6. And y is going to be minus 3, probably about there. So our graph is going to look something like, and I better get this right first time because if I'm going to have to delete, it's going to be rough. So it's going to look a bit. Oh, sugar. It's going to look something a bit like this. No, not like that. It's a straight line. Oh god, it's awkward to draw with a digital pen. Yeah, delete it. Go on. No, don't delete the axis. Damn it. Uh, Something like that. Okay. Something like that. Obviously, I'll draw it a bit cleaner, but obviously you get the point. It looks like that. And actually, I don't. That's a really detailed sketch that shows all the information you need. However, it's only 2 marks, I believe, so I think you could just draw the shape of it and roughly where the turning point is. Okay, we did all that then. So then it says briefly explain why C does not include all the points of this. Okay, so uh, okay, let's just they asked you to sketch the curve first of all. That might be a key point. They probably did that for a reason. Uh, and then we go to II. Hang on, I need to plug my laptop in. Uh, there we go. Okay, so that's what the graph looks like. All the what's it? All the points on C. No, all C does not contain all the points on that. Okay. Okay. Uh, okay, we can get rid of this now, I think. So this is going to be a thinker. This is. Okay, so we know what this curve looks like, right? We know what the x and the y points look like. It has that graph, right? Uh, okay, but notice this value. Yes, notice this here. This is a key point here. X is in real, so that means X can be absolutely any number you can think of. Okay. Obviously root 2, a million, 1,000 minus e to the, I don't know, minus 0 point a million. Any value you can think of. That's what that means. But actually, if you look here, and this goes back to like the range and domain sort of situation here, we have this expression here for x, and we only have a certain values for t here. Now, if we were to be precise here, well, sine t has to be between -1 and 1. Okay, so that would mean 3 plus 2 sine t has to be between. Well, we double it, -2 and 2, add 3, so that would be 1 to 5, right? That would be the bounds, and actually, this is the same as x. So this is actually saying what 1 is less than x less than 5. So actually, what's happening here is the y values might indeed actually no, um, and it's the same sort of argument with y as well. So cos 2t has to be again between -1 and 1. So then, likewise, 4 plus 2 cos 2t. Uh, damn it, let's get rid of it. So then the double cos 2 cos 2t between that, so 2 cos 2t, double the n, so -2 to 2, and then add 4 to both sides. So -2 add 4 will be 2, and then 2 add 4 will be 6. So what this is saying is actually, if you combine this, so this is y. So it's saying that this original parametric equation, which is the curve C, actually, it's saying that both, let's get rid of this, 1 is less than x, x is between 1 and 5, right? Because of how the range of sine and cos t works. And y is between 2 is less than y is less than 6. However, if you go back to the graph, well, the graph here looks like this, right? It's kind of what's saying about negative and positive infinity, actually, with the range. Actually, x for this curve here, because x is real, you pick any, it has all, x value goes beyond this. It encompasses every possible x value, right? Same with y goes to infinity and negative. Well, no, y is bounded by the maximum and negative infinity, right? So it's really just a question about the domain and range, essentially, is what this part boils down to. So what I guess in essence, what I'm saying is the x value, I guess in particular, is actually bounded between 1 and 5 because of this here, because of the sine t, how sine t is between 1 and -1. However, in reality, it's saying this point here, all the points on here, it encompasses all x values. But here, there's only a subset of x values, only a selection. X can only be between 1 and 5, but here it's saying x can be absolutely anything at all. So for that reason, it won't include all points on this curve with this x for any value of x. It will only have this curve here, C, can only be choosing x values between 1 and 5. Same way with y in a way. But yeah, so for that reason, we would encompass all values of y. So I guess to write that, the parametric equations on C means that 1 is between x5 since -1 is between sine t and 1. So what was it? 1 is less than or equal to, what was it? 2 sine, what was it? 1 at 3 plus 2 sine t. Okay. Which is less than 5, which you worked out. Which is x, so 3 plus 2 sine t. It's not really clear, is it? Let's get rid of all this. What am I doing? Oh, now you want to copy and paste stuff. Could have done with that earlier. uh, what was it? 1. So 1 is between 3 plus 2 sine t over 5. Um. Okay. Yeah. So that's where that comes from. However, on what did it say? Did it just give the equation? Or what? Did it say anything else? Does not include all points on that. Okay. Yeah. So what's it? 6 minus x minus 3 squared. Okay. On y 6 minus x minus 3 squared. X uh it takes any real value of x, so includes more values than uh than that, so it includes values, sorry, god damn it, outside the interval 1 less than x less than 5 on C. Okay, so C doesn't include all points. Okay. Oh, that's the end of the answer. Oh God. I'm gonna need to make more room then because there's another question. God, they don't give you much space for this question, do they? Yeah. So if you want something like that, and obviously the y values differ as well, because of the same sort of logic. Obviously, we've seen y has to be above 2, but obviously when we sketch the quadratic, y can sink below 2. So again, it encompasses more y values as well. So C doesn't include in that respect as well. So you can phrase it, you can phrase it in a similar sort of way as long as you express that the value, the points on C are bounded. However, so they're only between a certain interval. However, the points on this curve are unbound. You can pick any value you want. However, on this curve, you can only pick a certain range of points. That's kind of the idea you want to get at, essentially. So I might delete that actually. Yeah, it's 5 marks. I'm going to need to make room. I'm actually going to get rid of these two, so hopefully people have got this. I don't know. No, I'll leave the sketch there. That might help actually. But I'm going to delete all this. Uh, Actually, no, I'm not. I'll tell you what. Actually, no, I'm not actually. How do I? I'll tell you what I'll do. No, don't delete all this. God. Oh, God damn it. I was going to get a blank page to write on. But God damn it, I think it's gone now. Let's just put the sketch down again. Uh, there you go, something like this. Really wonky though. Okay, let's get rid of this then. God. There we are. Okay, so I'm going to do the last part of the question on the blank page. Leave the rest of the work in there. You don't read it. Weird. You get a lot of space for the other questions, but this one they're just skimping on it. Let's do a blank document. Okay. So I presume this is going to be the killer question. I assume. Let's go there. So let's see what the question says. So the line with equation x plus y is k intersects c. So bear in mind c is this equation here, not this. Okay. At two distinct points, state the range of values of k. Give writing your answer in set notation. Okay, so there's some stuff to think about here. So again, it comes. You're really gonna need to pay attention to this range here. You really are. Because what you might be tempted to think is just substitute the discriminant. Do the discriminant thing like we did earlier in the paper. So say look what y is k minus x. Substitute y into this equation here, say, and then do the discriminant, and then get the value of k, and then say set the discriminant to be above zero because it's two distant points. However, the discriminant works on the quadratic for real for all values of x when x is real. But what we've already discussed in part two is that x is actually on C, actually only between a certain amount of values. So the discriminant won't factor in the fact we're only looking at a certain interval of x. So the discriminant test, if you will, the discriminant thing, won't really work on this one. So we're going to have to think of a different way of finding k. Okay, so um, uh, but yes, so we can reason graphically. So we sketched the curve, and this is a line, so we can kind of look at it graphically. So, but we also know all points on C have to satisfy this. So what we can actually do is almost get a snippet of the graph on part B and only focus on these values of x and y. So we've actually done quite a lot of the work already, actually, with reasoning in part I. So we know that 1 is between x and 5 on C, and 2 is between Y and what was it? And 6. Okay. We also know the curve. So then we know the curve on part B. That's -3. The curve would look like that. So that's what was it? 3 plus root 6. Was it? Is that right? I can't remember. No, that's 3 minus root 6, sorry. Uh, and that'll be 3 plus root 6. And the turning point is 3, 6, if I remember correctly. Yeah, that's the information we got from the graph. Uh, yeah, so 3 minus root 6, 3 plus root 6. You're probably right about that. And that's our turning point at 3, 6. Cool, so that's the same information. I think that's all the information we really need, actually. But obviously, like I said before, x is real, which means x goes to all values on the spectrum, from minus infinity to infinity. Same with y. Well, the maximum value of y is 6, but it goes to minus infinity if we keep continuing on the graph. But actually, what we want to do is kind of condense and snippet the graph, because we only want to look at the values when x is between 1 and 5 and when y is 2 and 6. And actually, so once we do that, the battle's already done. Let so we need to really focus on when x is between 1 and 5. So if you noticed, before, 3 minus root 6 was 0.55 something. So actually, the curve is going to start a bit above the x-axis. Okay, so it's going to start there. And when x is 1, so I should probably also write down the curve as well. So y is 6 minus x minus 3 squared, right? I believe. Let's head back up. 6 minus, yes. Okay, so that's that. And it starts at 1. So if you plug in x equals 1, y would be, so to make sure check y falls in this range. 6, oh god, it's getting dark now. I need to turn my light on actually. Y is going to be 6 minus 1 minus 3 squared. Gets you 2, bang on the dot. Lovely, lovely. So actually, the curve starts here, and and bear in mind this was also 3 plus root 6, was it? Let's check back. That's actually 5 point something, if we remember. Well, I think I've deleted it now, haven't I? I could have done the question there. Oh well. Yeah, I'll tell you what I'll do though. After I finish the stream, I'll write it up on this paper and then save it as one document. Maybe I'll publish a document as, I don't know. Uh, no, I don't have it. But if you put it on the calculator anyway, 3 plus root 6, so the other intersect, is 5.449 something. So actually, the curve also finishes a bit before it intersects again, so it's going to be like there as well. So x is 5, 1. I should say that's 3 minus root 6, and that's going to be 3 plus root 6. Okay, so that's all the bounds of x1. Y, obviously it ascends to 2. So when does it drop back to 2? Let's have a look. It should be 5, I think. So 6 minus 5 minus 3 squared gets you 2. So when x is 5, y gets you 2 as well, which makes sense, because if our x values are right, then that means our y value should be right as well. Okay. So yeah, that's essentially what we want to look at. That's the condensed cropped curve. Okay. Actually, make the curve a bit better. So that's 2. Obviously, y goes up to 6 there, so that's still going to be 3. And actually, I don't know, an interesting observation, I guess. It's slightly symmetrical, I think, with this new version. Well, it is symmetrical. Obviously, around the turning point, symmetrical. Anyway, I'm waffling there. But that's basically what you want to do. This is what the curve sees, and actually, you can kind of do this with part B as well. If you wanted to reason geometrically, this is the curve C, and this is what the curve this equation looks like. So notice how you're cutting out certain points. So notice all the curves on this. They're not all on this curve because we cut it out. Um, Okay, and specifically, this is what happens when x and y are real numbers that we can pick. Where here, x is in the interval 1 and 5, and y is between 2 and 6. But anyway, that's the curve we're looking for. So what this is saying is, go back to the question, that's the curve we want to look at. That curve, let's go back. That curve, so this line intersects C at two distinct points. So y plus x plus y is k, and it intersects at 2 points. And it intersects this curve, not this curve, but this curve at 2 points. At two distinct points. Okay. Okay, so I guess you could say y is minus x plus k. So actually, really, y minus x would look like this. So that's y is that y minus x, I believe, would obviously cross for the origin. Would look like, let's say, okay, something like that. Obviously, it goes through the origin. Uh, yeah, so it looks like that. So essentially, what we need to, and this is where you need to need to look at it graphically. This is where it gets tricky. Um, so minus x, but all we're doing is we're saying what k. Now, if you think about if we add k tells me how many units we shift the line up or down, essentially. But the curve have always have this, the lines sorry have this gradient. So I don't want to sketch it. I'll do another sketch actually. So what is happening geometrically is uh, so we have this curve here, which is here, sketch. And that's saying our y is minus x is that. So what we want to keep shifting this, right, until it finally crosses the curve twice, essentially. And as you can see, there'll be two different intersections. That's what we want to do here, essentially. Okay. Okay, and that's essentially what we want to do. We want to find the cut-off point between this point and when it reaches like here, when it only crosses it once. And that's what we really need to do, I guess. And that's where we need to put our thinking caps on. And I'm going to need a new document here as well. Uh, yes. Okay. What's going on here? Okay, there we are. Okay. Hmm. Okay. And also bear in mind, this is why you wouldn't do the discriminant as well. Because say if we use the original curve here, if we just subbed it in and use discriminant, if we drawn the line down here, it would cross here and here, but obviously that's out of the range. So it would give us the wrong value here. So that's why you can't use the discriminant because it factors in, like I said, all values of x. That's when you can use the discriminant. When you need to only look at certain values of x, you can't use it for this exact reason. Okay. Uh. Okay. If we look at the graph, then right, this is where you argue graphically. Obviously it's going to reach the left side of the curve first, right? But using this, if we shift it up, but it's going to hit the left first, and then the right side of the curve after the turning point. It's going to hit that later, right? So what? I don't know how to explain this. So this line here, in order to ensure it hits at two distinct points, we need to make sure it also hits the final point there here at the end point here. Now this end point is 5 2. Okay, so what we need to ensure is consider the point where uh, the line here intersects 5 2. So if we said at 5 2, wow, 2 would equal minus 5 plus k, which means k would be 7. So that's saying if we shifted it 7 points up, which kind of makes sense, it would how to explain this? It would be so here. Hang on, let's get rid of this line here. It will always hit the left side first here, right? But if we need to shift it up such that it then hits this, okay, and it'll hit the right side at this point first. So, and then once we hit this point here, bang on. If we then keep shifting it up, it will always ensure we have two distinct values. So this means, first of all, k has to be strictly greater than 7 to ensure we get two distinct values. Right? But then, obviously, when we keep shifting it, it's going to get to a point eventually where it's going to only intersect it once at like this point here, say, and then everything above that value, it's not going to hit it at all. So actually, we need to look at the upper value of k as well. So if we shift it too high, then it won't hit the curve at all. So we need to shift this point down, but we need to work out what value of k intersects with what this point kind of is. So we've got the lower limit of k, but there's going to be an upper limit as well. Um, hmm. Uh, hmm. Okay, interesting. Well, I guess it's symmetrical, right? Uh, around this point here. So I think what we could also think, where does it when K7? What are the points of intersection? This is where we need a new document. So K7, that would mean y is minus x plus 7. We also know that y is 6 minus x minus 3 squared. Uh, So therefore, minus x plus 7 is 6 minus x squared minus 6x plus 9. So then minus x plus 7 equals 6 minus x squared minus 6x plus 9, and then x squared plus 5x plus 6x minus x plus 5x plus 9. Well, that would be minus 9, wouldn't it? Minus x squared. Oh, that'd be positive 6x, wouldn't it? Okay, hang on, I need to check here. This is wrong. X squared minus 6 minus 7x plus 16 equals 0. Solve this. Hopefully one of the x values should be 5. Use the calculator. Oh, we've got imaginary. Oh, hang on, we've messed up there. X squared minus 6x plus 9. I'm not getting the right values here, so the quadratic must be wrong. Minus x plus 7. Yeah, super check. Yeah, k would be 7 here, right? Let's have a look. Yes, because obviously it's going to hit the right, the furthest right point here, which is that 5, 2. So then substitute 5, 2 in, as we did. 2 would be minus 5 plus k, so k would have to be 7. And then k. I think k can be greater than or equal to 7, I think. Because if it's still 7, it would still hit the point. But it would still hit this as well. So it'd be 2, so it'd be greater than or equal to 7. Bear in mind, being more specific. So then k7, y would be minus x plus 7. And then that's a simultaneous equation. 6 minus x. Is the curve right? 6 minus. 6 minus. Yes. Okay. Yeah, so what's going wrong here? 6 minus x squared. 6 minus x squared plus 6x minus 9. So then x squared goes on this side. Minus x minus 6x minus 7. Oh, here, constant here. So 7. Okay, that's why. We didn't include the 6 there for some reason. 9 plus 7 is 16. Minus 6 plus 10. There we are. 1. Okay, yes, so you get x is 5. X is 2. That's a very interesting observation. Okay. So it's saying, actually, this shows the curve might be a bit off. So it's saying, when k7, it intersects when x is 2 and when x is 5. But that makes no sense because that would have to be like a flat curve. If it has to cross with both of these points, it would be a flat line. That can't be true because it's minus x. It's not horizontal. So why is it saying 2 here? Okay, I expect x is. Oh, no, 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 no. Ah, no, because that's not the end point. Sorry. No, 1 is the point here. This is 2. So this is x is 5. And this is 2, not 1. 1 is the end point. There we go. Okay, so. What this is, why we work that out? Why did we work that out? Because it's symmetrical. So, uh, it first crosses the curve at x is 1. So it's saying for when there is like a 1 unit difference between when it crosses the left side and the right side. That's what that's saying. Right, left or right to the turning point, anyway. Um, so I believe because the turning point is free, you can only increase K one more time before then it just crosses the turning point. Hang on. I don't know how to explain this the best way. I'm probably waffling a lot. But again, this shows the process of working out, right? I'm not just giving you like done it all and then give you a like a pre-packaged working out explanation. I'm working out as we go along, which I think is more valuable. So yeah, when K7 it crosses both sides. Uh, but we know if we add one more value to Y, oh no, sorry. No, so hmm, what's the midpoint here? No, I think I'm in a bit too lost here. Anyway, K7 here, and it intersects at 2 and 5 at X. Okay. Okay. When does it first cross this side? Actually, well, I guess think about. I think I'm over complicating it. I think so. It will keep crossing the left and the right side to the turning point. However, once it then crosses through the turning point, it will only have like one intersection. No, I don't think it's at the turning. Okay, see this is what I'm thinking now. Uh, I'm thinking of substituting as a little, play around with it. 5-2. Uh, the turning point is 3-6. So x3y6. So that would mean x plus what was it? X plus y equals k. Therefore, k would be 9. Okay, what you can do, I think what we can do now is kind of see that if there's only one point of I don't know why would there. I don't think so. I guess think of it like this. Say this is a turning point now. In theory, it could still cross it twice, right? So no, it's the wrong sort of. I don't think that's right though because say You could still do that on both sides. So I guess then the point you'd want to figure out is this point here, where it sticks out. Hmm. Anyway, let's see what happens. So what I'm going to propose to do, obviously, uh, is substitute x, y is 9 minus x into here. So it's going to be this, right, it's going to be the exact same quadratic, except uh, if we are adding 2, so 9 instead of 7, this is going to be plus 12, I believe. So there's not much work we need to do here. 1 minus 7. Uh, yes, that'd be 12. And actually, you still get 2 points of intersection. Yeah, so it's like that arg. So if say turning point is not the best one. So it doesn't only intersect once at the turning point. So yeah, it's a bit above the what on the right side still. Let's see, yeah, it's not it's not the best way of looking at it. Okay, that's not the right way. Um, okay, so that's not necessarily the right sketch either. That's not the right. So basically, what I'm trying to work out here is I'm trying to sketch on the right side of the turning point. But obviously, it's not meant to go up; it's meant to go down. There we go. Something like this. So I reckon the line would still cross. So say this is the turning point here. It will still cross 2 points, but we need to work out this little like bit that sticks out of it. That where that point is. Uh, so how do you reason this? So we reason this because it's the right side. Uh, I guess okay, just visual it geometrically. I guess so. The line is just keep shifting up and up and up. Uh, to there. Hmm. Hmm. It's a real good question, isn't it? Yeah, this is definitely just for the top A-star students for sure. You can see why it's a final question. I'd reckon we get like 2 to 3 marks for getting this, but we need to work out the upper limit. So, what value of k, uh, such that if we go any further, it will only intersect once and go above the curve. But what this is a situation that's going on. This is a bit. This is really not accurate. It's like it. It'll go like this. So we need to find out this little arc bit there. This point where if we move any higher, it will only cross it once. Hmm. It's a thinker. It really is. Oh, I guess some people are like, oh, I got 97 out of 100. That's perfect for me. But I guess this is to show everything. uh, hmm. Yeah, but people do this in time conditions. If you are really, really good if you do this in time conditions, like 5 minutes, because it's got 5 marks. So yeah. Hmm. Okay. I've got. I'm gonna try a different idea. It's gonna be really weird, but hang on. So if you look at the for this one, if you if you consider this whole graph, right, even the normal version with all the x and y values, even uh obviously if we it will intersect twice, even if we pick that k's that are less than if we go down, but surely the maximum value when k because k will only k will start to cross it once in the same cut. How do I reason this? So k, if we like draw a line there, for instance, it would the point where k intersects twice to once, it will be the same point on both the curves, right? It will have to be at this section of the curve. That's what I'm saying. Basically, what I'm saying is the point where k there's only one or zero intersection of the curve will be at the same point. Uh, so what I'm proposing is, and obviously, k increases each time. So what I'm proposing is actually really weird, but it might work. So to work out the upper limit of k, so the k so basically the upper limit of k will be the same for both curves. The lower limit will be different. What I'm proposing is we actually consider the function as a whole. Uh, oh god. So what I'm saying is, so what is it? Y is 6 minus 3x. Uh, let's get rid of all this because this is waffle pretty much. So what I'm proposing is, oh, for God's sake, and this might be a lot of work for 5 marks, but we'll see. It might get us the answer. So well, we know that y equals 6 minus x minus 3 squared. That's the curve. And y is minus x plus k. What I'm proposing now, we actually intersect and do the discriminant. But watch. Uh, so minus x plus k would be 6 minus x squared minus 6x plus 9. Which equals 6 minus x squared plus 6x minus 9. Therefore, x squared minus 7x plus One was yes. So I'm just I was daydreaming that. I don't know why. 6 minus 9 would be -3. Add that, so that'd be +3 plus k, I believe. Now, actually, if we do the discriminant here, so what the idea is here, we can actually use this. You have to be selective when using discriminant. If we use a discriminant for this curve here, and we equate it to the line y, the y equals x plus k. Actually, if we do the discriminant, that tells us if we set it to be 1, that tells us the point where here. This tells us this point here when we find a discriminant, solve it for 1, where b squared minus 4ac equals 0. When there's only one intersection, that's going to happen here. That's going to be where k reaches the curve, and anything above that value of k is going to go over the curve. I'll explain that better. So actually, you can use discriminant here to work out the point where the curve the tangent, not the tangent, the line goes above the curve. So yeah, discriminant implies that 49 minus 7 squared minus 4, 1, 3 plus k equals 0. 49 minus 12 minus 4k equals 0. That would then tell you 4k would be 37, k would be 37 over 4, which doesn't simplify, I don't think. And yeah, that's it. So what that's just telling you is the point where the curve literally goes once. That is when k is 37 over 4. If k goes anywhere above 37 over 4 because of our knowledge of graphs, if we translate or shift this line above 37 over 4, it will not touch the curve. And because that will be the same as this. Okay. Uh, so actually, that's our lower. So when there's only one distinct point of intersection, that's k 37 over 4. But to ensure that still distinct points of intersection, k has to be strictly less than 37 over 4. Okay, so then if we shifted it a bit down, again, like here, say, there'd still be 2 points here, right? So actually, our final, if we combine both our reasoning together, it would actually be 7 less than equal to k less than 37 over 4. And that's our answer. However, I remember, just to find a part, the final caveat, set notation. So, I'm going to get rid of this here. This little bit, I'm just equating them. Answer. So, in set notation, it would be for A level, you don't really need to know sets, really. Just know it'd be x such that set k, sorry, not x, k such that 7 less than equal to k is less than 37 over 4. But how you'd properly do a set is really it should be k in the reals. So any value of k in a real value, such that 7 is less than k. So what the set is saying is, so this is the brace. It's like a bracket. This is giving you a set, essentially. It's giving you all the possible values of something. And we want all the possible values of k, which are real. You don't really need that. You just say k. All the values of k. So this is what it's saying. The set of all the values of k, such that the two dots mean such that, so a condition, and then the inequality. So that's what the set is saying. But for A level, just know that it's kind of worked like this. So as long as you know to put the curly braces and then the X such that and the dot, it's pretty much the same. But that's your true final answer, I believe. Let me just check that's right because I did a lot there. And then if it is right, Then I'll try and explain it more clearly before I leave it there. But yeah, like if you did that in 5 minutes, wow, hats off. Oh, I've lost it now. Let me look at the mark scheme for that. I hope that's right. Did all of that and then it. Oh, got to look at it again. Final question. Yes, 9 point. Yes, 37 over 4. Yes, 7 between K and 37 over 4, and you have to with the exact inequality. Yeah, so I got it right. Okay, so I mean, I got the answer. That's the answer. So you can leave it there now, I guess, if you wanted to. But if we're going to explain it more succinctly, okay, how do I want to explain this last part? Because this is like the true A-star question. And I did see a similar question like this in another past paper as well. So you know what, it's not too bad to learn this sort of thing. So this question, the reason why it makes it hard is because you can't just willy-nilly use a discriminant. You have to be conscious of when you use it. Be- the main reason being is because we have limits on x. We can't have because x in this curve anyway isn't the whole reals, isn't every possible value. You can't just blindly use a discriminant like with other questions. Okay, how do I explain this? So obviously this is x plus y is k, and if we increase or decrease k, increasing k shifts the line up, decreasing shifts it down. So uh, if we were to just use the discriminant for this curve, the general curve, without cutting it down to this, this is C. This is not C, mainly because of our domain here. But anyway, if we used it on this curve here, um, what would happen is, no matter what, every say even down here, you would have two intersections no matter what, because the curve keeps going down and down. So the only time K, so the only time K would have, uh, the line would have one or no intersections is when it goes above the curve up here, and that's when we can use a discriminant to work out the upper value of when the curve goes above the line. Okay, the line goes above the curve even. So if we shift K enough units up, it will go above the curve here, like there, for example, right here. If we go like above here, it goes above this point here, it would not intersect at all. So can you use a discriminant? If you were to use a discriminant like we did, uh, if we it would only intersect. Like I said, like we used a discriminant. If we set it to 0, the only time there's only one intersection is there, right, at that one point. But actually, there's a lower limit as well because unlike this is where it differentiates. Pun intended. No pun intended. Sorry. But there's a lower limit as well, like we discussed down here. So the upper limit of K you work out the discriminant because the it coincides with the two graphs, so it'd be the same. So you can just use a discriminant there. However, the key difference between these two graphs, so this is a graph we're interested in, um, it's only a subset of values. It's only a certain interval values for x, right? It's a cropped graph, right? So actually, if we these are like various values of k. If we shift the line up or down, values of k. Actually, because we cut off the curve, there's actually also points where there's another region where the line would not intersect the curve, simply because we cut off part of the curve, right? So even if we go down certain values of k, if we shift the line down, instead of up, there'll also be places where the line, the x plus y equals k, would not cross the curve at all. But notice if we go down here, this line, and then we shift it up by some values of k, eventually it will start crossing that curve. So actually, and notice it will hit the left side of the curve first, and the first time it will cross the curve twice is at this very point here. If you just look at it geometrically, if you keep shifting, almost place a ruler. Say like if you put a ruler here, if you shift the ruler, push it straight up, it would cross this point first. So that's when it crosses this end point here, which is at x is 5. That's the first point. It'll have two distinct intersections with the curve. But then if you keep shifting it up, like we said, eventually it's going to reach here, and there'll only be one point, and then eventually it won't intersect the curve when you go up. So hopefully that explains it. So you the curve, if we the line y minus x plus k, if say we had it down here, we'd have to keep shifting it up until it crosses the curve. It will cross the curve twice when it has the endpoint here. This endpoint is the lower value of k that we have, and then if you keep shifting it up here, eventually it will get. If you shift it up and up and up, eventually it will also leave the curve here, which you can work out as a discriminant. Okay. So hopefully that wraps it up. So to work out the endpoint here, obviously that's the endpoint here, 2 and 5 here, and then substitute in to get the k, and then k has to be above 7, or it can be 7 because even if it intersects the endpoint, it will still intersect the left side as well. So we have two distinct points there. But then eventually it will only intersect the curve once up here, and then it leaves it. So you need to make sure, and this happens with when k was 37/4. So that's one intersection point. So you need to make sure it's less than to make sure it still hits it twice. Hopefully that makes some sort of. I know that's really confusing, and I probably didn't explain it the right way. But hopefully that made some sort of sense here. Hopefully the key takeaway is to A, recognise the distinction between the curve here and this curve, because we only interested in certain values of x and y, and B, because of that we can't just blindly use a discriminant to find the values of k. Yes, we can use it from the upper limit of k, because it will the point where k the line leaves the curve up here is the same as when it leaves here. So we can use the discriminant here, because the discriminant only works when you can use any value of x. When you start restricting values of x, the discriminant won't always work to give you values of k or anything like that. So you have to be careful. So that's the two key takeaways really. Realize when a discriminant fails and why you can't use it here blindly, and why the curves are different, because you're taking different domains, different values of x. Okay. And yeah, so really that's it. So you have to, and because of that, you need to think geometrically as well. So like I said, to plot the line, plot the curve, and then think about what happens if you keep shifting it up. When does it first cross the curve twice, which will be here, and then when does it leave the curve? So it'd be up here, and actually it will leave the curve again, to reiterate, in this graph as well at the same point. So because this graph is for all values of x, then you can use a discriminant test. When you only have certain values of x, you need to be careful. And I'll say that because there was another question on another past paper where it asked you again similarly to you to like another line, and it asked you to find the values of k again. But you couldn't use a discriminant because x was bounded. It only gave you a subsection of the graph. It only gave you that instead of fully completing it. So it's very similar to this. I think it's 2024, 2023 paper. I'm not sure. but it does come up time and time again. With questions like this, which really, really test your knowledge. So you really have to understand domain. You need to understand the discriminant, and stuff like that. When you cannot use it. Okay, so this question is very, very, very tricky. Very tricky. This is why it's the last question in the paper for the top A-star students, especially if you're in the time limit as well. This question really, really tests your geometric understanding. So the lines and when things cross, and you have to play around with it a bit and use your think visually. And also, you need to think critically as well. Like I said, you need to consider the curves, why they're different, of when you cannot use discriminant. Hopefully, I'm not going to say too much there to confuse you, but hopefully, with that explanation, you get what's happening with this question here, particularly this part C here, and why it leads to the answer. Okay, there's a lot of stuff that play with this final part of the question. That's why it's the last question. Hopefully, that made some sort of sense. If anyone does have any questions, I can maybe do a follow-up video to this particular question and explain it better if I can explain it better. If anyone's confused by that. But yeah, don't be too harsh on yourself. It's a very, very. This is definitely by far the hardest question in the paper, and rightly so because it's the final question. So yeah, that is definitely the final question. I'm going to leave that there then. Yeah. Yeah. Very, very. Yeah. I like that paper actually. Yeah. Final. Not too bad. And like I said, I think for most students with that question, you'd still get like 2 marks if you just use the discriminant the normal way. So you still get some of the marks if you even if you didn't fully understand the question, if you will. But yeah, I think that's how you would approach the question. What I said there, like I said, the other bits of the paper aren't too bad. Most of it is quite you'd see in other past papers in the textbook or whatever. But that last part of the question really makes you think, uh, and it really separates the A-star students from the rest. But yeah, hopefully that explanation made sense. That's how you'd want to approach that. So yeah, this question, the key central idea of this question is noticing x is real and when x is only certain values. Okay, that's the key idea of this question, and like I said, understanding domain and range is a really key topic as well, which students struggle with, which I might cover at another point. But yeah, I'm going to leave that. Hopefully, it made any questions with any questions about any of the questions. uh, just comment or whatever. I'm not trying my best to answer it if I can. But that's the paper. I haven't really checked. I really checked the mark scheme for a few questions that I thought were a bit iffy. But if there are any mistakes, I probably might be. Like I said, I am rusty. I haven't done maths in years since my studies. I haven't really, and like I said, sometimes the handwriting's a bit messy. It's my first time using a pad. But yeah, any question you want me to clarify anything or whatever, with this paper or anything else with maths, just let me know, comment, I'll try my best to answer it. But yeah, hopefully that made sense. I don't know, hopefully it made sense. Like I said, the whole idea of this is not really just to be a marks game, but to actually go through the paper and uh, explain my thought processes, what you should be thinking, what should be striking to you when you see the question. So with every question, the topic you should be thinking what topic it is, what can I do, and stuff like that, and break it down. So going through the process essentially, I think is very helpful rather than just giving the answer. And yeah, and obviously it takes time as well because obviously this is what that like 5-ish hours. Obviously, you wouldn't expect five to spend 5 hours on it. I was carefully explaining the concepts and stuff like that. So obviously it'd be quicker than this in normal exams. Obviously you only get 2 hours. Uh, but yeah, hopefully that was too bad. I don't think that was too bad of a paper. I think the grade boundaries for that year were what 230 was it? I don't think, apart from what a very few questions, I think a lot of the questions are quite accessible if you practice past papers before. Well, anyway, I'm going to leave that there. And I'm going to stop waffling. I'm going to upload this. It'll be on YouTube, it'll be on the playlist. It'll be in the math section. Like I said, any questions was asked. But I am going to leave that there then for now. Also, let me know. I guess you want me to upload this mess of a PDF my workings on. But I don't know if that's of interest. Let me know. But I'm going to leave that there then for now.